A silence stretches over the North Pole, broken only by the faint groan of shifting ice and the distant echo of unseen waters. Beneath kilometres of glaciers, vast expanses remain untouched and inscrutable, hiding landscapes and forces that defy comprehension. The reasons for this absence are not merely practical, they are rooted in the Arctic's concealed mysteries, from subterranean ridges to tremors that ripple beneath the ice, each layer presenting enigmas that have left even the most determined explorers hesitant. Across frozen basins and under towering ice sheets, expeditions trace invisible fractures and record the pulse of hidden seismic activity. You will encounter subglacial currents that shift unpredictably, methane plumes rising from unseen fissures, and regions where sonar maps reveal only fragments of reality, each observation deepening the Arctic's chilling mysteries. The ocean that replaced the myth. At the very top of the planet, where maps converge into a single point, the ice appears solid and absolute. For centuries it was imagined as the frozen cap of a hidden continent, a final piece of land awaiting discovery. The reason we're not exploring beneath the North Pole's glaciers begins here, with a revelation that overturned expectation. There is no continent beneath the pole, only a shifting lid of sea ice covering a deep and largely unseen ocean. What was once thought to conceal land instead conceals water, depth, and a seabed far below, presenting a challenge few have attempted to confront directly. For much of early European exploration, the Arctic was approached with geographic certainty. Cartographers speculated about polar landmasses, and some believed a temperate sea might exist at the world's apex. By the 19th century, expeditions sponsored by Britain and the United States pressed northward through the Canadian Arctic archipelago, expecting that solid ground might anchor the pole. Yet as explorers pushed farther into the drifting ice, they found no mountains, no coastline, no bedrock rising toward the surface. The ice moved, cracked, and reformed, revealing that it was not attached to land at all, leaving observers to confront the stark possibility that the pole rested entirely upon a floating unseen ocean. That realization matured slowly. In 1896, the Norwegian explorer Fridtjof Nansen allowed his ship, the Fram, to freeze deliberately into the Arctic pack ice. Nansen's theory was that the ice itself drifted across an ocean basin, carrying vessels with it. Over 3 years, Fram's path confirmed that the ice moved across deep water rather than over shallow continental ground. Soundings taken during the expedition measured depths exceeding 3,000 metres, evidence that the North Pole rested above an oceanic abyss rather than a hidden landmass. The expedition's journals recorded how unpredictable ice shifts could throw measurements off course in hours, underscoring the difficulty of any sustained operation above open water. Those measurements altered more than maps. They transformed the very nature of polar exploration. If the pole was ocean, then reaching it required traversing a floating, unstable platform of ice rather than marching across terrain. When American explorer Robert Peary claimed to have reached the North Pole in 1909, he did so by travelling over sea ice that drifted beneath his sleds. Whatever precise coordinates he achieved, the surface under him was not fixed earth but frozen ocean moving silently over deep water. Each step taken across the ice was temporary, each camp a fragile perch on a transient surface. By the mid-20th century, technological advances finally allowed explorers to confirm what lay directly beneath the pole. In 1958, the American nuclear submarine USS Nautilus completed the first under-ice transit of the Arctic Ocean, passing beneath the geographic North Pole. Its instruments recorded ocean depths and under-ice contours that left little doubt. The pole was suspended above a vast marine basin. The following year, USS Skate surfaced through thin ice near the pole itself, further confirming the absence of land. These missions revealed a complex topography of underwater ridges, trenches and basins, most of which had never been charted and remained difficult to access. The Arctic Ocean, unlike Antarctica, does not rest upon a continental mass at its centre. Instead, it is divided into deep basins separated by submerged ridges. The central basin near the pole reaches depths of more than 4,000 metres. This depth presents a fundamental complication. Exploring beneath the North Pole's glaciers is not a matter of drilling through ice into soil, but of penetrating thick sea ice, descending through kilometres of frigid water, and operating in an environment where pressure, darkness, and remoteness converge. Each operation must contend with extreme cold, crushing water pressure, and complete absence of natural light, demanding highly specialized vessels and instruments. Sea ice at the pole is typically between 2 and 4 meters thick, though pressure ridges can extend much deeper. Beneath that ice lies the Arctic Ocean, whose waters remain near freezing temperatures year-round. Unlike land-based ice sheets, such as those covering Antarctica, Arctic sea ice drifts continuously under the influence of wind and currents. The ice cap rotates slowly in a pattern known as the Beaufort Gyre, and it also participates in a transpolar drift that carries ice from Siberia toward Greenland. Any structure placed atop this ice moves unpredictably, often requiring constant repositioning, and small errors can render carefully plotted scientific work useless. This drifting surface creates an absence of permanence. There is no stable platform from which to establish long-term drilling operations directly at the pole. The ice fractures into leads, ridges and flows, rearranging itself with seasonal cycles and storms. Expeditions that once established temporary camps near the pole did so knowing that their position would not remain fixed. The Soviet Union operated drifting research stations beginning in 1937, including North Pole 1, which collected valuable meteorological and oceanographic data while floating across the Arctic basin. Even these stations were temporary, carried by currents rather than anchored to Earth, and many were lost when ice floes fractured unexpectedly. The absence of land also complicates the question of jurisdiction and infrastructure. On land, nations construct research bases, airstrips, and permanent observatories. At the North Pole, there is nothing to build upon except ice that may crack without warning. Beneath that ice lies international water governed by maritime law, not sovereign territory. Exploration must therefore contend not only with engineering difficulty, but with the legal and logistical reality of operating over deep ocean in one of the most remote regions on Earth. Establishing long-term observatories is not only technically challenging but diplomatically sensitive. Antarctica provides a telling contrast. There, the South Pole rests atop a continental ice sheet nearly 3 kilometers thick, beneath which lies solid ground. Scientists have drilled deep ice cores at stations like Amundsen Scott, retrieving climate records extending back hundreds of thousands of years. At the North Pole, equivalent drilling would require stabilizing equipment on moving sea ice and then lowering instruments through water thousands of meters deep before reaching sediment. The technological challenge multiplies, and with it the cost and risk. Equipment that functions well on Antarctic ice often fails when suspended above the ocean. Oceanographic exploration has advanced significantly in recent decades, yet even modern research vessels cannot maintain position at the pole without continuous adjustment. Icebreakers can carve temporary paths through pack ice, but the cleared channels close quickly as the ice shifts. Autonomous underwater vehicles offer promise, but deploying and retrieving them through unstable ice requires carefully controlled openings. Communication systems must operate in high latitudes, where satellite coverage has historically been less reliable, adding another layer of uncertainty. Every expedition is measured against the possibility that the ice itself will erase months of meticulous work. The result is a paradox. The North Pole is geographically central, symbolically powerful, and frequently visited by aircraft and icebreakers, yet the seabed directly beneath it remains comparatively understudied. Sonar mapping conducted by submarines and research expeditions has revealed broad contours of the Arctic basin, but a high-resolution, continuous study of the exact area beneath the pole has been limited. Each mission gathers fragments of data rather than sustained observation, constrained by the fact that there is no fixed ground from which to operate, and every piece of information carries a margin of uncertainty shaped by drifting ice, shifting currents, and uncharted depths. What replaced the myth of a polar continent was not simply an ocean, but an environment that resists permanence. The revelation that the pole floats above deep water redefined exploration as a transient endeavour. Researchers can pass through, measure, and record, yet they cannot easily remain. The ice that conceals the ocean also denies stability, and the ocean beneath demands equipment designed for abyssal depth rather than terrestrial excavation. The surface itself is as elusive as what lies below, leaving the central Arctic a realm of partial knowledge and enduring mystery. The ocean below waits silently, indifferent to the explorers who cannot stay long enough to know its secrets. the ridge beneath the Arctic ceiling. Across the Arctic basin, the Lomonosov Ridge stretches like a shadowy backbone, its form largely unseen and complicating every attempt to explore under the North Pole's glaciers. Beneath the drifting sea ice, this underwater formation rises thousands of meters from the ocean floor, creating a barrier to the deep surveys that explorers and scientists have long attempted. Despite repeated expeditions, the ridge remains partially unmapped, an enigma whose shape and structure challenge instruments, navigators, and the very methods used to study the Arctic. It is this hidden topography that forms one of the clearest reasons why the glaciers above it are rarely penetrated, and it casts a silent dominion over every mission that dares approach. Early cartographers glimpsed the ridge not through sight but through faint distortions in primitive sonar readings, a spectral outline that defied conventional seafloor models. These initial anomalies appeared in charts from the 1940s and 1950s, yet they were treated with skepticism. Even as data accumulated, the ridge did not present itself as a simple underwater plateau or continuous slope. Instead, it seemed fragmented, a series of rises and valleys stretching across the central Arctic. Each line on a sonar display hinted at something real, yet so alien that surveyors questioned the reliability of the instruments themselves, unsure whether they were charting stone or illusions shaped by water and ice. During the Cold War, both Soviet and American submarines passed over the ridge, gathering fragmentary data that hinted at vast unmapped elevations below. Missions were conducted in secrecy, and only small portions of the sonar readings were declassified decades later. Analysts studying these fragments noticed irregularities that were difficult to reconcile with known oceanography: abrupt slopes, strange undulations, and zones where acoustic waves behaved unpredictably. Whatever lay beneath the ridge, it was not only distant and deep, but it was resistant to human comprehension, an environment in which technology seemed to falter at every attempt to chart it fully, leaving maps permanently incomplete. Modern mapping technologies still struggle to render the ridge in full, as ice drift, unpredictable currents, and fleeting survey windows layer uncertainty onto every measurement. Even with icebreakers and autonomous submersibles, the Arctic's shifting conditions make it nearly impossible to maintain precise positioning for continuous observation. Satellite altimetry provides only broad approximations of the seafloor, while sonar scans can be misled by variations in water density, temperature, or under-ice topography. Each expedition relies on brief windows of calm weather and stable ice, yet these moments are fleeting, emphasizing the ridge's defiance of human timelines. Shrouded in darkness and cold, the ridge rises through the Arctic waters as a series of unexpected peaks and troughs, appearing almost mountainous when measured by sonar, yet its contours shift with each pass. Submersible missions record formations that can appear to extend endlessly, only for the next pass to reveal sudden gaps or distortions. The ridge's irregularity is compounded by the thickness of the overlying ice and the extreme pressures of the deep ocean. Even modern vehicles designed for under-ice navigation must contend with these constantly changing topographies, and each observation can raise new questions rather than offer clarity. Ocean temperature and pressure around the ridge fluctuate unpredictably, complicating the deployment of instruments and limiting the time researchers can spend observing its features. Cold currents swirl along its flanks, sometimes accelerating unexpectedly and creating turbulence strong enough to force submersibles to adjust course. Thermoclines shift in ways that distort sonar readings, producing echoes that appear as ridges where there are none and masking real formations. The ridge seems to exert a quiet, relentless influence over its environment, shaping water, pressure and temperature in ways that remain poorly understood even today. Magnetic irregularities above and near the ridge distort navigation instruments, rendering precise positioning a persistent challenge for vessels attempting under-ice operations. Compasses can deviate unpredictably, and even modern GPS systems are subject to intermittent errors at extreme latitudes. Submarines have reported minor course corrections of several kilometers in areas mapped over the ridge, highlighting the challenge of aligning scientific measurements with actual geographic coordinates. These anomalies add another invisible obstacle to exploration, one that underscores how the ridge's presence shapes human perception of the Arctic beneath the ice. Sediment cores recovered from the ridge's flanks reveal abrupt geological transitions, hinting at tectonic upheavals and glacial cycles that remain only partially understood. Layers of crushed rock, clay, and compacted sediment suggest episodes of extreme pressure and movement, possibly connected to shifts in the Arctic's ice cover over millennia. Some strata appear displaced or fractured, implying events that modern science has not fully explained. These samples are tantalizing fragments of a history written in stone and silt, yet they offer only glimpses into a world too deep and remote to examine comprehensively. Strong undercurrents sweep along the ridge, displacing autonomous submersibles and forcing researchers to abandon or modify planned missions without warning. The combination of depth, fluctuating pressures, and water movement creates conditions that no single expedition has been able to control fully. Engineers and scientists must continuously recalibrate instruments, adapt to shifting currents, and accept the possibility that some areas of the ridge will remain unreachable. Even minor miscalculations can result in lost equipment or failed data collection, leaving the ridge perpetually partly unseen. Sonar reflections bouncing from the ridge produce ghostly echoes that blur the line between real formations and illusions, leaving every chart open to interpretation. Analysts have observed ridges that appear to float above the seafloor, peaks that vanish on subsequent passes, and troughs that deepen without warning. These phenomena raise questions about the interplay of water density, ice overhead, and sonar wave behavior. The ridge's contours are thus not just physically elusive, they distort perception itself, reinforcing the sense that the Arctic conceals a domain deliberately resistant to human measurement. Ice formation above the ridge is subtly influenced by the topography below, producing pressure ridges and leads that make surface travel and scientific operations unpredictable. The floating ice can crack and shift along the underlying contours, creating channels or ridges in unexpected locations. Temporary observation camps or drill sites may be carried away by currents, and icebreakers must constantly adapt to these hidden forces. Even the surface, often thought to be navigable, mirrors the ridge's stubborn complexity, reminding explorers that every expedition depends on the unknowable. Despite intense international interest, political sensitivities, and unclear Arctic jurisdiction, restrict collaboration and limit comprehensive exploration of the ridge's most enigmatic sections. Although the region falls largely under international waters, the history of military expeditions and competing territorial claims has created a climate of caution. Researchers often must navigate diplomatic constraints, classified data, and operational limits, which further slow or prevent sustained study. Every step toward understanding the ridge is thus as much a political negotiation as a scientific one, leaving large sections unexamined. Each new measurement or survey over the ridge seems to reveal more questions than answers, reinforcing the sense of an inaccessible world where every discovery deepens the unknown. Peaks, troughs, currents, and anomalies combine into a complex puzzle, with each expedition producing a new layer of partial knowledge rather than clarity. For every ridge mapped or sample collected, a dozen mysteries remain: variations in depth, unusual sediment patterns, unexpected currents, and sonar distortions. The ridge, despite centuries of Arctic exploration, endures as a domain where the unknown outweighs what is understood, a spine of mystery under a frozen ocean. The ridge endures beneath the polar waters, a silent spine whose secrets resist every attempt to uncover them. The geological argument no one has settled. The frozen Arctic conceals a debate that refuses resolution. Whether the glaciers above rest on a stable foundation or a fractured, unknowable seafloor, scientists and explorers alike have long been confronted by conflicting evidence, each new expedition producing partial insights that raise as many questions as they answer. Instruments provide hints of peaks and valleys, yet their readings are distorted by water density, ice thickness, and under-ice currents. The unresolved nature of the seafloor beneath the North Pole is not merely a technical challenge. It forms a profound obstacle to understanding the Arctic's hidden architecture, making exploration beneath the glaciers a venture fraught with uncertainty and forcing researchers to question every assumption about the landscape they think they know. During the early 20th century, explorers recorded unusual formations on the Arctic seabed, but without precise instruments, these observations became fragments of an incomplete geological puzzle. Reports of ridges, depressions, and irregular terrain were often dismissed or misinterpreted, leaving a legacy of partial and sometimes contradictory records. Even the most detailed surveys could capture only snapshots of the environment, and early expeditions had little ability to differentiate between sediment accumulation, submerged rock, or ice-formed features. The scattered observations hinted at a world of complexity far beyond the scope of contemporary science, a seafloor whose contours seemed to change subtly with each observation. Geophysicists surveying the Arctic's magnetic field have encountered readings that contradict one another, hinting at anomalies whose origins remain speculative and unexplained. Certain areas show rapid fluctuations or localized disturbances, suggesting the presence of unusual mineral deposits or tectonic irregularities. Others indicate no discernible pattern at all, creating zones of confusion that challenge mapping and navigation. These conflicting measurements have fueled decades of debate among scientists, none of whom have produced a definitive explanation for the distortions that pervade the region, leaving entire swaths of Arctic territory in a state of permanent mystery. Sediment cores extracted under the ice yield conflicting clues. Some layers suggest stability over millennia, while others reveal sudden upheavals that defy conventional interpretation. Geologists studying these cores find evidence of repeated glacial advances and retreats, interspersed with sediment that appears disrupted or displaced in ways that hint at dramatic geological events. The cores contain fossils, crushed rock, and compacted silt, each layer telling a story that is partially legible but never complete. Together, they suggest a complex dynamic underworld beneath the Arctic ice, one that is only partially understood even by the most experienced researchers and hints at processes far beyond human observation. Tectonic activity models for the North Pole vary widely. Some propose slow incremental shifts, while others imply hidden forces capable of sudden dramatic movements. The ridge and surrounding seabed have been theorized as both stable and unstable, with measurements giving conflicting impressions of stress and strain in the crust. Subtle earthquakes recorded in the area, though rare, lend weight to the possibility that sudden geological change is possible. Yet the evidence remains patchy, leaving the question of stability unresolved and exploration attempts inherently risky. For planners of scientific missions, this uncertainty dictates caution, forcing a constant reassessment of what areas can safely be investigated. Mapping subglacial features has revealed irregular formations that challenge standard geological classification, producing charts that specialists debate endlessly. Peaks rise unexpectedly from the ocean floor, troughs deepen without warning, and formations appear where no theory predicts them. Some anomalies might be glacial in origin, others tectonic, but certainty is elusive. These maps are both tantalizing and frustrating. They suggest a pattern while simultaneously revealing how much remains unknown, emphasizing the Arctic as a domain that refuses straightforward interpretation. Each new map seems to contradict the last, as though the landscape itself is mutable or resistant to human measurement. Ocean currents and pressure variations over these formations complicate interpretation, producing signals in sonar and seismic surveys that appear both real and illusory. Instruments often record echoes that vanish or shift on subsequent passes, creating confusion over whether a peak is a physical feature or a reflection. Seasonal changes in temperature and salinity further distort readings, while ice movements overhead scatter acoustic waves unpredictably. Even advanced technology cannot completely overcome the interplay of natural forces that obfuscates the true shape of the seafloor, forcing scientists to rely on tentative conclusions and provisional theories. Scientists face a paradox of partial evidence, enough to suggest patterns, yet never sufficient to confirm them, leaving the geological narrative perpetually unresolved. Sediment layers may align with one hypothesis while sonar readings support another. Magnetic anomalies hint at substructures that have never been directly observed. Each new piece of data illuminates certain questions while deepening others, leaving researchers in a continual state of investigation, careful to avoid conclusions that the next expedition might immediately contradict. In some cases, instruments fail in high-pressure, low-temperature zones, adding yet another layer of mystery. Computer simulations of glacial and seafloor interactions produce conflicting projections, emphasizing the gap between theory and observable reality. Models can predict the flow of ice and movement of sediments under certain assumptions, yet real-world measurements rarely conform to these simulations. The result is a persistent tension between expected behavior and the phenomena recorded during fieldwork. For scientists, This contradiction serves as a reminder that the Arctic resists simplification, that its geological story is layered, unpredictable, and often at odds with human attempts to codify it, leaving entire hypotheses perpetually unresolved. Field expeditions often return with data that contradict earlier measurements, reinforcing the sense that the Arctic conceals forces science cannot yet quantify. Ice drilling, sonar mapping, and seismic monitoring each provide snapshots, but those snapshots rarely align seamlessly. One survey may indicate stability, while the next reveals unexpected displacement or previously undetected ridges. These contradictions make planning long-term research extremely challenging, and for many the uncertainty alone is reason enough to limit under-ice exploration. Even years of consecutive measurements fail to produce a consistent pattern. Movements of ice, sediment displacement, and under-ice pressure ridges interact in ways that remain poorly understood, creating a maze where every answer leads to further questions. Even subtle shifts can obscure features or generate anomalies that seem to appear spontaneously. Researchers document these phenomena carefully, yet the combined effects of glacial dynamics, seafloor topography, and ocean currents produce patterns that defy simple explanation. The Arctic becomes a laboratory of paradoxes, a place where every discovery introduces new uncertainty instead of closure. International collaboration has yielded tantalizing hints of consensus, but geopolitical sensitivities and extreme conditions prevent definitive conclusions about the Arctic's hidden geology. Joint missions and shared datasets offer partial clarity, yet legal disputes over sovereignty and the logistical limits of extreme latitudes constrain comprehensive exploration. As a result, much of the debate remains theoretical, with researchers piecing together a narrative from incomplete fragments, simulations, and intermittent field measurements. The geological argument persists unresolved, waiting for future generations of scientists to weigh competing evidence while the ice silently shifts above. Every new survey or experiment seems to deepen the uncertainty, reminding geologists that the North Pole is less a site to be fully mapped than a riddle to be continuously examined. Peaks, troughs, and anomalies appear and vanish in datasets. Sediment layers contradict one another, and tectonic indicators oscillate between stability and hidden force. The Arctic is both an archive and a puzzle, preserving evidence yet frustrating every attempt at definitive interpretation. Exploration under its glaciers remains limited not by equipment alone, but by the enduring indecision embedded in the Earth itself, a caution that every geologist must respect. Even after centuries of study, the Arctic's foundation resists certainty, as though the Earth itself guards its secrets beneath layers of ice and time. The submarine missions still classified. Few records exist of the submarines that once glided silently beneath the Arctic ice, their movements obscured by the shroud of national secrecy and Cold War caution. These missions were never intended for public knowledge, yet traces of their existence hint at a hidden history of human presence under the polar cap. Navigation was fraught with peril, as crews moved through uncharted ice tunnels and unknown pressures, relying on instruments that could fail without warning. The Arctic beneath the glaciers was no longer simply a natural frontier. It became a domain where politics, strategy, and secrecy determined who could witness its depths. Every decision taken on these missions reflected a careful balance between exploration and the imperative of concealment, leaving the public unaware of what truly lay beneath. Early under-ice missions were often brief, constrained by extreme conditions, yet every sortie hinted at landscapes and formations never intended to be revealed. Captains reported long stretches of water where ice formed ceilings overhead, rising and lowering unpredictably with tides and currents. Instruments would register unexpected depth changes, pressure spikes, and anomalies in magnetic readings, which could suggest anything from geological formations to previously unseen features. The combination of harsh environment and incomplete technology meant that even partial observations could alter scientific and strategic understanding, yet none were ever fully published. Personal logs, often coded or heavily redacted, hint at unusual encounters, leaving fragments of a story intentionally incomplete. Sonar echoes recorded by these vessels sometimes returned anomalous readings, suggesting ridges or depressions that remain unexplained decades later. Analysts attempting to interpret these signals found inconsistencies between different passes, as if the ice itself conspired to obscure the true shape of the terrain. Some anomalies hinted at features that did not match known geological patterns, creating questions that no civilian survey could answer. These echoes were catalogued meticulously, yet for decades they remained classified, leaving a tantalizing record of what might lie beneath the frozen surface. Even decades later, researchers studying public records find themselves chasing shadows of measurements they cannot verify. Engineers of the era struggled to adapt submersible technology to a world of shifting ice, where pressure and cold could render instruments unreliable within moments. Hulls were reinforced, sonar arrays recalibrated, and nuclear power used to extend operational range, yet the Arctic environment consistently exposed the limits of human invention. Even minor miscalculations could result in severe consequences. Unexpected ice ridges or pressure variations could damage equipment and endanger crews. The technical achievements of these missions were remarkable, but much of their knowledge never left the walls of secure facilities. Each advancement seemed to reveal as much uncertainty as it did capability. Many of the maps produced during these missions were classified almost immediately, leaving only fragments of their data available for public scrutiny. Sketches of sub-ice passages, sonar profiles of ridges, and notes on ice thickness exist only in archives inaccessible to most researchers. Scientists working in the Arctic often had to rely on partial information, interpolating from incomplete records or comparing outdated surveys. The secrecy surrounding these missions ensured that some areas of the Arctic remain effectively off-limits, not because of ice or ocean hazards, but because human authorities have chosen to withhold the details of their navigation. These restrictions created a parallel geography, where some regions exist only in the memory of those who navigated them. The few declassified photographs and logs hint at objects or geological structures that do not appear in civilian surveys, provoking both curiosity and frustration. In some images, shadows suggest angular shapes or ridges that cannot be reconciled with known formations. Logs describe corridors of ice and water where submarines navigated with care, avoiding hazards that were never documented publicly. Every fragment raises more questions than answers. Why were these features omitted from later surveys, and what did those in command hope to conceal? The Arctic's under-ice world thus became a stage for both discovery and deliberate obscurity. Some observations suggest passages that could connect vast areas under the ice, though no map confirms this. Modern submarines have expanded the reach of Arctic exploration, yet the majority of their findings remain restricted under government confidentiality agreements. Even with advanced sonar, satellite navigation and remote sensing, the public remains largely unaware of the discoveries these vessels have made. When declassified information emerges, it often confirms earlier anomalies without clarifying them, perpetuating a sense that the Arctic holds secrets beyond both natural and scientific comprehension. Researchers are left with glimpses rather than full understanding, constrained by restrictions that are political as much as logistical. The Arctic, in effect, remains partially mapped, partially imagined, and largely forbidden. Reports occasionally leak, describing corridors beneath thick ice where no vessel should safely traverse. But verification is impossible and speculation forbidden. Journalists and researchers piece together fragments from memoirs, interviews, and declassified materials, but inconsistencies abound. Some passages appear repeatedly in multiple accounts, yet their precise location and dimensions remain unclear. These whispered corridors form an invisible map, one that only insiders could navigate fully, highlighting the persistent inaccessibility of areas where classified operations have ventured. Each rumour, however small, underscores that human choice, not just ice, is what conceals these regions. Crews recount sensations of navigating a vast alien underworld where ice forms ceilings and shadows obscure even the most reliable instrumentation. The psychological strain of isolation, extreme cold, and complete darkness intensified the sense of mystery. Instruments that usually guide navigation became unreliable, and every echo or anomaly could indicate either a natural feature or a hazard unseen. Accounts of these experiences, when partially declassified, emphasize that exploration under the North Pole glaciers is as much a test of human endurance and judgment as it is of technology. Many veterans of these missions describe a haunting sense of the Arctic as alive, constantly shifting and indifferent to observation. The combination of sonar distortion, ice movement, and deliberate operational secrecy produces a landscape that is both partially observed and intentionally obscured. Data collected is often contradictory. Ridges appear in one survey, vanish in the next. Sonar signatures fluctuate, and logs record events that others cannot verify. These discrepancies are amplified by the deliberate omission of sensitive information, creating a situation where the Arctic is both explored and unknowable at the same time. Scientists and historians alike confront a paradox. The more the Arctic is probed, the more its secrets appear safeguarded. The ice conceals not only its own forms, but the imprint of human restraint. Even international scientific collaborations face barriers when classified missions intersect with open research, leaving gaps that cannot be reconciled. Agreements allow some shared data, but security concerns prevent full disclosure. Observations from one nation's submarine may not align with another's published research, producing a mosaic of knowledge full of blanks and uncertainties. These gaps are not merely inconvenient, they actively shape our understanding of the Arctic, leaving large areas effectively invisible to exploration despite technological advances and repeated missions. Every collaboration carries the risk that some information will remain inaccessible indefinitely. Submersibles occasionally document unexpected thermal vents or pressure anomalies, yet the details remain inaccessible, locked behind security protocols that outlast any expedition. Scientists have long speculated about unusual features under the Arctic ice, but only fragments ever emerge, often years later, and never in complete form. These partial revelations fuel curiosity, hint at risks, and emphasize that Arctic exploration is constrained not just by ice or depth, but by the discretion of those who control access to its secrets. Even minor discoveries can remain classified for decades, their impact on science delayed indefinitely. Attempts to cross-reference historical logs with modern sonar often reveal discrepancies, implying either lost knowledge or events deliberately erased from public record. Features once recorded in classified missions sometimes fail to appear in contemporary surveys, suggesting either natural change or intentional obfuscation. Researchers are forced to reconcile these mismatched datasets without access to the full archive, a task that underlines the enduring opacity surrounding under-ice exploration and the unseen activities that continue to shape the region. Some corridors may exist only as traces in memory and classified records. Each mission's secrecy compounds the mystery, emphasizing that some areas beneath the Arctic ice are uncharted not due to danger alone, but because humans have chosen that they remain so. The result is a layered enigma, natural complexity intertwined with deliberate restriction. Where explorers might assume access is physically impossible, it is often legally and politically prohibited, leaving a human-shaped void in the map of the North Pole. The Arctic thus remains a realm of both environmental and informational obscurity, where curiosity meets the limits imposed by authority. It is a region where knowledge itself is as frozen as the ice above it. Some corridors of the Arctic are closed not by ice or ocean, but by the invisible walls of secrecy that no explorer may breach. The 2007 descent that released only fragments. The 2007 descent promised unprecedented access to the Arctic under-ice world, yet what emerged above the surface were only fragments of its true story. The expedition, undertaken with advanced submersibles, was heralded as a milestone in polar exploration, but the public learned almost nothing of what was observed. Sonar maps, photographs, and data logs were released selectively, leaving enormous gaps in understanding. The descent revealed that even with modern technology, the Arctic retains regions that resist full documentation, where environmental complexity and operational caution conspire to obscure what lies beneath. Observers would have to interpret shadows, echoes, and partial images, a task both fascinating and frustrating in its incompleteness. The sparse fragments suggested formations that challenged assumptions about under-ice topography and hinted at hidden corridors of unknown extent. Weeks of preparation had preceded the dive, from calibrating submersible instruments to charting provisional ice corridors, every step designed to confront an environment few had penetrated. Engineers and scientists worked in unison, anticipating extreme pressure fluctuations and rapid temperature changes that could compromise both vehicle and crew. Drills simulated emergencies, and each technical system was subjected to redundancy checks. Yet no simulation could capture the precise behavior of the Arctic beneath the glaciers. The crew understood that the descent was as much a test of human adaptability as of machine resilience, and that much of the under-ice world would remain enigmatic even in the best-case scenario. Every calibration, every rehearsal, was an attempt to reduce risk in a realm that seemed determined to remain partially unseen. Engineers monitored temperature gradients and ice thickness with meticulous care, aware that even minor miscalculations could render the descent catastrophic. The ice above the submersible was often unstable, shifting imperceptibly and creating pockets of unpredictable pressure. Sensors were constantly adjusted to accommodate these variations, yet they produced their own distortions and occasional anomalies. The team documented every measurement in anticipation of later analysis, fully aware that only a portion of this material would be available for scientific or public review. Even within these careful constraints, each reading hinted at patterns that did not conform neatly to previous Arctic data, suggesting the presence of previously unrecorded features that teased the limits of exploration. When the submersible finally pierced the ice, its hull vibrating against unseen pressures, the crew entered a world simultaneously familiar and alien in its silence. Shadows stretched across the water, refracted by layers of ice above and currents below. Every instrument registered minute fluctuations that suggested hidden ridges or depressions, yet none could provide definitive confirmation. Visibility was limited, forcing reliance on partial sonar returns and fragmentary images. The descent was a confrontation with the Arctic's unwillingness to be fully catalogued, a domain where even the best-prepared explorers could only glimpse isolated segments of the terrain. The submersible became a moving lens, glimpsing what could be documented and leaving the rest to speculation. Early sonar sweeps revealed unexpected variations in the seafloor, patterns that suggested structures or depressions that had not appeared in prior surveys. Some anomalies hinted at abrupt shifts in depth, others at angular formations that contradicted assumptions about the region's geology. Analysts monitoring the descent speculated over the origin of these patterns, knowing full well that few of their questions would ever be answered. Each sweep produced data that was both promising and enigmatic, a combination that underscored how little was truly understood beneath the North Pole glaciers, despite decades of research. Even seemingly minor deviations raised questions about ice movement, sediment deposition, or other unknown factors influencing the under-ice landscape. The mission's cameras recorded images of angular shadows and strange formations, yet only a small portion of this footage was ever released to the public. Some images appeared to capture ridge-like protrusions or depressions, while others were dominated by ambiguous textures of ice and sediment. Researchers analysing the released materials noted inconsistencies between frames and intervals, suggesting that large areas had either not been captured or were withheld. These fragments provoked speculation about what remained unseen and emphasised the partial nature of human knowledge in the region. A few frames hinted at continuity across large distances, implying passages or depressions that the descent could only touch briefly before moving on. Data streams transmitted during the dive contained gaps and anomalies, hinting at features the submersible could not map fully, leaving scientists to speculate on what remained unobserved. Pressure readings fluctuated inexplicably, and acoustic signals returned patterns that defied immediate interpretation. Even minor irregularities in these streams suggested complex under-ice structures or dynamic phenomena that modern instruments could not completely resolve. The gaps in data became a narrative in themselves, a series of unanswered questions that reflected both the technical limitations of exploration and the Arctic's enduring mystery. Researchers noted that these gaps often coincided with areas of apparent topographical complexity, reinforcing the notion that some parts of the Arctic resist systematic study. Observers at the surface noted that readings fluctuated in ways that could not be explained solely by ice movement or water currents, implying either sensor limits or unknown topography. Some sonar blips suggested cavities, while others hinted at sudden changes in depth inconsistent with prior mapping. The contrast between expected measurements and real-time observations produced a sense of uncertainty that accompanied the mission from beginning to end. Every anomaly reinforced the idea that the Arctic is not fully knowable through conventional methods, and that even fragmentary glimpses must be approached with caution and skepticism. The crew understood that each reading represented only part of a larger unseen reality. Logs recovered later referenced passages and chambers that had never appeared on charts, but the descriptions were cryptic and heavily redacted. Some entries suggested corridors or depressions beneath the ice, while others referenced pressure anomalies and acoustic echoes of unknown origin. Analysts working with these logs attempted to correlate them with released footage, but the incomplete nature of the material left many connections unresolved. The mission, in essence, revealed both the potential of modern exploration and the enduring presence of secrets the Arctic has yet to yield. Even minor details hinted at features too vast or delicate to be captured fully, reinforcing the sense of fragmentary revelation. Analysts attempting to cross-check the fragments against previous Arctic surveys found inconsistencies that fueled both curiosity and frustration. Features noted during the 2007 descent did not always appear in earlier sonar surveys, raising questions about temporal changes, misinterpretation, or selective disclosure. Researchers were forced to construct partial hypotheses, often relying on educated guesses rather than complete evidence. The contrast between what was technically observed and what was publicly disclosed highlighted the tension between achievement and opacity in Arctic exploration. Each cross-check emphasized that our knowledge remains incomplete, as though only part of the Arctic's story has ever surfaced. Thermal anomalies and subtle acoustic echoes hinted at pockets of unusual activity, yet the fragmented nature of the release meant confirmation was impossible. Some readings suggested currents interacting with irregular ice formations, while others implied deeper, unexplored channels beneath the glaciers. Scientists could only speculate on the causes, knowing that the absence of complete data made definitive conclusions unattainable. These anomalies underscored the Arctic's layered complexity, where partial understanding serves to both illuminate and conceal the environment. The mission's fragments suggested patterns that may never be fully explained or understood. Even the mission's partial findings suggested a landscape of complexity and variation that modern instruments could touch but never fully resolve. Sediment patterns, acoustic reflections, and shadows in the recorded footage painted a picture of a world with multiple scales of relief and unexpected features. Each fragment seemed to imply more than could be confirmed, creating a persistent tension between knowledge and uncertainty. The descent became a reminder that even technological advancement cannot entirely overcome the Arctic's natural elusiveness. Every partial observation emphasized the vastness of what remained beyond human reach. Researchers continue to debate the meaning of what was released, aware that each fragment represents both a discovery and a deliberate limitation on what is known. Conferences and publications dissect the released data, but the conversation is constrained by gaps that prevent definitive interpretation. Every fragment hints at a world more intricate and inaccessible than the surface evidence allows, perpetuating the notion that Arctic exploration is always partial, mediated by both nature and human decision. Curiosity persists, tempered by recognition of the ice's intractable silence. Even decades later, analysts still return to these fragments in hopes of drawing connections that may never exist. The Arctic remains, in effect, only partially revealed, its depths teeming with detail that may never fully emerge from beneath the ice. Each mission, each fragmentary dataset, and each image represents a small window into a vast and concealed environment. The 2007 descent exemplifies the challenge. Even with preparation, technology, and skill, the Arctic offers glimpses rather than complete narratives. Knowledge is shaped by both what is observed and what is withheld, leaving a region that is technologically accessible but epistemically elusive. The fragments that did return suggest a world that continues to resist full comprehension, reminding all observers that the Arctic's heart is both near and unreachable. The descent had returned pieces of a world still mostly concealed, a puzzle whose heart refuses to surface. Sonar echoes without clear structure. Across recent surveys, sonar instruments have recorded echoes that repeat without obvious logic, suggesting under-ice structures that defy conventional mapping. The signals, captured during repeated Arctic expeditions, hinted at depressions, ridges and cavities that did not correspond to prior topographical models. Analysts noted inconsistencies in the patterns, some fleeting and others persistent, creating a sense that the ice itself was actively shaping the way sound travelled. Even the clearest readings carried ambiguity, and scientists found themselves interpreting fragments rather than full landscapes. These echoes exemplify the persistent reason why exploration beneath the North Pole glaciers remains incomplete. Nature produces information that refuses definitive understanding. Modern acoustic arrays, calibrated to detect both minute ridges and broad depressions, encounter readings that fluctuate unpredictably as they scan the frozen waters. Engineers designed these arrays to resolve detail at centimetre scales, yet what returned from the Arctic often contradicted expectations. Shifting currents, variable ice thickness, and temperature gradients interfered with transmission, producing irregular patterns that were not simply noise. Each sweep delivered new, enigmatic impressions, forcing teams to reconsider how much of the under-ice world could truly be mapped. The technology was precise, but the environment was mercurial, producing echoes that simultaneously revealed and obscured the structures beneath. Technicians note that even small changes in water temperature or salinity can create interference, yet many anomalies appear independent of environmental conditions. Some readings suggested voids and depressions that should not have existed, while others hinted at abrupt formations cutting across the seabed. These variations persisted despite careful calibration and repeated verification. Scientists began to suspect that the irregularities were not artifacts, but rather reflections of genuine features whose scale and orientation remained unclear. The under-ice landscape was resisting coherence, and every signal raised more questions than it answered. During extended sweeps, some echoes appear to form sequences, only to dissolve when scanned from slightly different angles, frustrating attempts at interpretation. What seemed like continuous channels or walls would vanish when the sonar moved slightly, replaced by new formations that had not been visible before. The temporal instability of these echoes suggested either dynamic features in the ice and water, or limitations in the instrument's ability to resolve complex geometries. Observers struggled to determine whether the apparent structures were real or illusory, a challenge that emphasized the Arctic's unpredictable nature. Each dive returned a partial story, leaving researchers to interpret hints rather than full narratives. Analysts have catalogued these patterns meticulously, but cross-referencing different passes rarely produces consistent topographic models. Sonar maps often contradicted themselves, with ridges appearing on one sweep and disappearing on the next. Even when multiple submersibles traversed the same region, echoes failed to converge into a coherent representation. The result was a patchwork of data fragments, each reliable in isolation, yet incompatible when combined. This inherent inconsistency serves as a central barrier to exploration. The instruments may function perfectly, yet the landscape itself refuses to yield a unified image. In some areas, echoes suggest cavernous spaces or unusual depressions, yet nothing matches the expected geological formations of the Arctic seabed. Researchers speculated on possibilities. Perhaps ancient ice channels, sediment disruptions, or unknown under-ice geomorphology were creating these reflections. Some anomalies suggested depressions hundreds of meters deep, while others implied continuous ridges stretching over long distances. Attempts to reconcile the observations with geological expectations consistently fell short. The result was a series of unanswerable questions, each hinting at a hidden underworld that could not be fully surveyed or explained. Minor variations in sonar frequency sometimes produce radically different impressions, indicating that the medium itself, ice and water, may be interacting with sound in unpredictable ways. Lower frequencies revealed broad undulations, while higher frequencies captured fine ridges that often contradicted the broader patterns. These discrepancies were not merely technical curiosities. They revealed the Arctic environment's complexity, where ice layers, water density, and suspended sediments combine to distort even precise instruments. The echoes are a record of both reality and perception, documenting features while simultaneously confounding the observer's understanding. Scientific teams have hypothesized that shifting ice layers could create false impressions, yet even accounting for movement, anomalies persist across multiple surveys. Floating ice can refract and scatter sound, producing overlapping echoes that seem to trace continuous structures where none exist. However, anomalies remain in regions where ice drift is minimal, suggesting that some patterns represent genuine under-ice features. Researchers are left with a paradox. The Arctic is both measurable and inscrutable, producing information that resists complete interpretation. It is this resistance that reinforces why certain regions remain unexplored and poorly understood. Modelling these echoes often reveals fractal-like complexity, as if the under-ice landscape resists simplification or coherent mapping. Attempts to simulate the readings show repeating patterns at multiple scales, yet no model captures the full spectrum of anomalies. Each simulation illuminates a fraction of the landscape while producing new ambiguities elsewhere. The result is a map that is never final, a mosaic that hints at form but cannot resolve it. Explorers confront a paradox in which precision and uncertainty coexist, and sonar becomes a tool that both reveals and conceals. Historical sonar data occasionally aligns with modern readings, but gaps and contradictions leave the exact structures unconfirmed, maintaining the mystery. Some ridges or depressions hinted at decades ago reappear, yet often shifted or altered, leaving no continuity between past and present measurements. These inconsistencies suggest dynamic processes or unknown structural complexities beneath the ice. Researchers attempting to reconcile old and new data confront incomplete narratives, where fragments of information suggest coherence that may not exist. The sonar, while revealing, refuses to provide clarity. Explorers report that navigating areas with these anomalous echoes is challenging, as instruments provide signals that cannot reliably guide submersibles or remotely operated vehicles. Signals may indicate open water in one direction but suggest a barrier in another. Even experienced pilots must rely on intuition and prior experience, blending limited data with cautious judgment. These constraints make deep exploration perilous, reinforcing the Arctic's reputation as a domain where technology meets its limits. Each dive is an exercise in uncertainty, guided by fragments rather than certainty. Some anomalies suggest continuous ridges or channels, while others imply abrupt shifts or voids, producing maps that cannot reconcile all observations simultaneously. The contrast between expectation and observation underscores the gap between human understanding and the Arctic's realities. Explorers attempt to impose structure on what is fundamentally unstructured, yet each attempt only highlights the complexity and unpredictability of the under-ice environment. The echoes suggest patterns without providing conclusive form, leaving every mapped area simultaneously familiar and alien. Even with advanced processing and machine learning algorithms, sonar images remain partial, fragmented, and open to interpretation, demonstrating the limits of human and technological perception. Computational techniques can enhance patterns or filter noise, yet no algorithm produces a definitive map of the terrain. The Arctic environment actively resists simplification, challenging assumptions that precise instruments guarantee comprehensive understanding. Fragmented signals dominate, reinforcing the sense that only pieces of a vast and unknowable landscape are ever visible. Every processing step adds clarity in one area while obscuring another. The Arctic's under-ice world, though increasingly measurable, still presents features that defy synthesis into a coherent, navigable structure. Echoes appear to suggest continuity yet vanish under scrutiny, giving rise to a landscape that exists partly in perception and partly in reality. The submersibles and instruments provide glimpses, but the overall architecture remains elusive. Each survey highlights both what can be known and what remains permanently beyond reach, demonstrating the central challenge of exploration in this domain. Structure is suggested but never fully resolved, a puzzle of sound and ice that persists in mystery. The ice whispers in signals our instruments can catch but never fully understand, leaving vast geometries perpetually beyond reach. The Arctic acoustic shadow zone. Sound sometimes vanishes entirely under the North Pole glaciers, slipping into areas that sonar and submersibles cannot penetrate. Instruments record nothing where echo should exist, leaving gaps in the mapping of the ice-covered ocean floor. Survey teams encounter these silent corridors repeatedly, with readings that simply do not correspond to known formations or expected topography. Each disappearance of signal raises questions. What lies within these acoustic voids, and why does the medium itself reject transmission? Some of the most precise arrays return only fragmented impressions, as though the water and ice conspire to distort the information before it reaches the observer. The Arctic, in these instances, becomes both measured and unknowable, demonstrating one of the most persistent reasons human exploration beneath the glaciers remains incomplete. These acoustic voids occur where water layers of differing temperature and salinity bend or absorb sound, producing gaps in detection that confound mapping efforts. Variations in density, combined with minute differences in ice thickness, create a refractive environment in which sound waves can bend upward, downward, or scatter unpredictably. Suspended microscopic particulates further scatter signals, creating echoes that appear as faint blurs or vanish entirely. Scientists have observed that these conditions are not uniform. They fluctuate seasonally and even daily, meaning that a corridor that appears silent one day might partially return echoes the next. Each observation confirms that the Arctic is not simply difficult to explore, it actively conceals itself with a complexity beyond current understanding. Scientists have long observed that ice thickness, subsurface currents, and suspended particulates interact with acoustic waves in complex, unpredictable ways. Microscopic ice crystals and sediment layers can absorb or scatter sound, producing irregular patterns that mask the true form of the ocean floor. Temperature gradients further complicate signal propagation, bending acoustic waves in directions that defy linear expectations. Even instruments designed to detect fine structures are confounded, producing returns that appear fractured, blurred, or inconsistent. Modern surveys often record these patterns as faint, fragmented traces, which may suggest structures that do not actually exist, emphasizing that the Arctic's acoustic environment is not just challenging, it is enigmatic. The silent corridors can stretch for hundreds of meters, sometimes forming channels where no instrument produces a coherent return, a phenomenon unique to the Arctic environment. Sonar sweeps, designed to provide continuous imaging, often reveal sequences that vanish mid-pass, leaving incomplete outlines of ridges or depressions. The abrupt disappearance of echoes suggests that the under-ice world may contain structures or phenomena that fundamentally resist acoustic interrogation. Researchers refer to these areas as corridors, not because they resemble any known feature, but because they hint at continuity within the discontinuity, a tantalizing mix of form and absence. Even in well-surveyed areas, the corridors shift subtly, suggesting that movement of the ice or current subtly alters the acoustic properties of the water, creating a constantly changing labyrinth. Signals frequently disappear mid-transmission, leaving instruments recording nothing where topography or ice formations should have produced echoes. Submersible operators describe a momentary sense of disorientation as expected returns vanish, and instruments display blank zones that cannot be interpreted as either open water or solid structure. This phenomenon has been confirmed repeatedly across independent expeditions, suggesting that the gaps are not equipment failure but a natural, if poorly understood, property of the Arctic environment. Some data even hint at the presence of sub-ice cavities, yet the absence of repeatable readings prevents confirmation, leaving only tantalizing traces that invite speculation without resolution. Even carefully calibrated sonar arrays fail to reconstruct the environment fully within these voids, generating maps that are incomplete and fragmented. Analysts are left to stitch together partial images, each containing reliable data yet failing to produce a coherent whole. In some cases, ridges suggested by one frequency disappear under another. Depressions hinted at by older passes are absent in current scans. The Arctic resists synthesis, reminding observers that precision instruments cannot guarantee knowledge where the medium itself actively reshapes signals. These repeated contradictions reinforce a sense of invisibility. For every observation that seems clear, a dozen others vanish into silence. Some echoes reflect partially, hinting at structures beyond reach, while others are entirely deflected, producing the sensation of a hidden labyrinth beneath the ice. Scientists speculate that these features may include sub-ice channels, ice keels, or sudden drops in the ocean floor, but the evidence is always incomplete. The deflected signals suggest boundaries and forms that exist only in the partial capture of sonar waves. In addition, the ice itself may act as a selective filter, reflecting some frequencies while absorbing others, producing a landscape that is perceptible only in fragments. As a result, every mapped area conveys both information and mystery, with gaps that challenge comprehension. Teams experimenting with varying frequencies, altering angles of emission and sensor depth, find that the silent corridors persist, resilient to every adjustment. Each alteration produces partial clarity, yet the overall pattern remains elusive, confirming that these acoustic voids are not artifacts but real, reproducible phenomena. Attempts to refine signal resolution merely highlight the paradox of measurement. The more finely tuned the instrument, the more apparent the missing information becomes. Even combining data from multiple vessels fails to produce coherence, leaving researchers with mosaics of incomplete echoes that hint at a greater form, never fully captured. Acoustic anomalies sometimes correlate with known ice ridges or depressions, but often occur where no surface features indicate any obstruction, deepening the mystery. Sound returns in ways that suggest a shape that cannot be confirmed visually or by other instruments, leaving researchers to infer structures indirectly. Some corridors appear aligned with underlying geology, while others float seemingly without cause beneath vast expanses of uniform ice. The irregularity of these returns suggests that the Arctic may possess properties that selectively manipulate sound, creating zones of concealment that remain impervious to human understanding. Submersible pilots describe entering regions where instruments offer no guidance, forcing navigation by intuition, memory, and minimal visual cues. In such conditions, even experienced operators proceed cautiously, knowing that instruments cannot be relied upon to avoid hazards. The silence of the void is more than absence. It is an active uncertainty, a space where exploration must blend skill with conjecture. These experiences underline why some areas remain inaccessible despite technological progress, reinforcing the Arctic's mystique and lending it a presence that seems almost sentient in its refusal to yield. The resulting uncertainty limits operational planning, as unmapped silent corridors introduce risks that cannot be mitigated by technology alone. Expedition leaders must schedule routes with wide margins for error, prepare for the unexpected, and accept that certain regions cannot be safely surveyed. Even sophisticated submersible designs and reinforced vessels cannot fully compensate for the lack of reliable acoustic information. The ice and water dictate the terms of engagement, leaving human ambition constrained by natural boundaries and environmental unpredictability. For researchers, these areas illustrate a paradox. Even the most sophisticated arrays are defeated by nature's complexity, highlighting both what is measurable and what remains unknowable. Data collection becomes an exercise in partial understanding, revealing some features while concealing others. Sonar traces provide tantalizing glimpses of structures, only to dissolve under further observation. The Arctic insists that exploration is never complete. Every advance produces new questions that instruments alone cannot answer. The persistent absence of data conveys as much meaning as the returns themselves, creating a landscape defined by silence as much as form. These voids are natural phenomena, yet they also serve as a persistent reminder that much of the Arctic remains impervious to human inquiry. The ice and water create conditions that prevent comprehensive mapping, leaving corridors that instruments cannot penetrate. Even with decades of research, these acoustic anomalies remain only partially understood, a testament to the limits of human perception and the deliberate complexity of the environment. Nature in these moments exerts control over the narrative of discovery, leaving explorers with a landscape that is revealed only in fleeting, partial impressions. The under-ice world transforms into a domain that listens selectively, a place where even sound itself hesitates before revealing secrets. The Arctic, in this sense, is not silent by accident but by design. The medium absorbs, refracts, and bends information in ways that leave the human observer always chasing fragments. Each expedition illuminates some corners while leaving others in deliberate obscurity, a testament to the interplay of measurable phenomena and enduring mystery. The corridors of silence are not merely gaps, they are the Arctic asserting that it cannot be fully known, that some aspects of the ice-covered deep exist only in the absence of sound. Some echoes vanish without trace, leaving corridors of silence that no human probe can breach. The unidentified low-frequency Arctic sounds. A deep, persistent vibration moves through the Arctic waters, registering on instruments yet eluding explanation. Hydrophones capture the low, rumbling hum as it spreads beneath the ice, sometimes appearing in pulses and sometimes as a continuous murmur. Observers aboard research vessels note that the signals arrive without discernible source, as if the ocean itself is generating a message that refuses human comprehension. Arrays record the activity in fragmented patterns, leaving analysts to wonder whether the sounds are natural phenomena, subtle geological shifts, or something entirely beyond known science. The Arctic seems to resonate with an intelligence that can be felt but never fully understood, as if it preserves knowledge older than any map or instrument. Hydrophones capture frequencies far below human hearing, forming a sonic pattern that appears deliberate yet cannot be traced. The signals drift unpredictably, sometimes lingering for hours before fading, then reappearing in distant areas. The low-frequency range allows vibrations to travel extraordinary distances through water, yet no correlating surface activity, ice movement, or sub-ice structure accounts for their appearance. In some cases, the pattern of pulses suggests a rhythm or sequence, hinting at a form of communication beyond conventional explanation. Each recording becomes a puzzle, a fragmentary glimpse of a sonic presence that the Arctic keeps largely hidden, an almost sentient presence that cannot be mapped. Observers have noted that environmental factors, temperature, salinity, and ice composition, affect propagation, but they do not fully account for the signal's irregular behaviour. Tiny variations in water density bend and refract sound in unpredictable ways, scattering signals or making them appear to originate from multiple directions simultaneously. Ice thickness, cracks, and subsurface currents further alter the path of the waves, producing echoes that arrive delayed or distorted. Despite accounting for all measurable variables, analysts find inconsistencies that defy expectation. The patterns remain persistent and unyielding, emphasizing that the Arctic is a medium with rules human understanding only partially grasps, a domain where conventional measurement fails. Sometimes the low hum pulses rhythmically, as if the ocean itself is sending messages in a hidden language. These rhythmic emissions suggest repetition or continuity, but no meaning can be discerned. Instruments register intervals that fluctuate subtly, never perfectly regular, creating a haunting cadence that hints at order within chaos. Onboard observers describe the experience as both mesmerizing and disorienting, as though listening to a signal meant for some other form of perception. Even the most advanced signal processing equipment fails to translate the low-frequency waves into recognizable sound patterns, leaving the Arctic's hidden voice to echo in mystery, reverberating long after the signal fades. Arrays spread across ice flows record shifts and convergences, hinting at sources that remain invisible to visual or sonar verification. The signals sometimes seem to converge, as if multiple origins synchronize briefly, then diverge as if withdrawing into separate corridors. These ephemeral alignments defy prediction, producing moments of clarity that vanish almost immediately. Cross-referencing with ice movement, subsea topography, and currents reveals no connection, deepening the sense that the sounds operate independently of known physical laws. The patterns are ephemeral, elusive, and constantly shifting, leaving only fleeting glimpses of their possible origin and reinforcing the impossibility of certainty. Certain emissions resemble tectonic activity or ice movements, yet the consistency and spectral composition challenge conventional explanations. The vibrations occasionally mimic the slow grinding of ice or the tremors of shifting plates, but in intervals that do not align with observed geological events. Spectral analysis shows harmonics and resonances unexpected for either icequakes or seismic activity. The persistent appearance of these frequencies, sometimes spanning weeks or months, adds a temporal complexity that further separates them from known natural events. In essence, the Arctic produces a sonic landscape that cannot be mapped fully or predicted reliably, a shifting composition that defies full comprehension. Other signals mimic patterns found in whale communication, but the extreme conditions of the Arctic make biological sources unlikely for many of the most pronounced occurrences. The low frequencies could travel long distances like whale calls, but no known species inhabit these depths in sufficient numbers, nor do their calls produce the precise spectral profiles observed. Occasionally faint echoes of familiar bioacoustic signatures emerge, but they are overwhelmed by vibrations that defy categorization. The auditory environment beneath the ice is layered with mystery, mixing the plausible with the inexplicable, leaving interpretation tantalizingly incomplete, a challenge that persists across seasons and expeditions. Efforts to triangulate the origins of these sounds yield conflicting coordinates, leaving those monitoring them with only partial or contradictory data. Signal paths bend and curve unpredictably, sometimes appearing to originate in one location only to later suggest another. Observers have attempted complex array configurations to isolate source points, but the signals resist localization. Even when multiple vessels record simultaneously, the supposed origin shifts subtly with environmental changes. The Arctic refuses precision, leaving the low-frequency phenomena as an enigma that no technological setup has yet fully resolved, an acoustic riddle embedded in the frozen depths. At times, one array detects activity while a nearby sensor registers silence, suggesting the signals interact unpredictably with water layers and currents. Thermal gradients and subtle density variations create corridors where sound is amplified or absorbed, producing pockets of silence that appear and vanish without warning. These effects make it nearly impossible to track or anticipate the movement of signals, forcing analysts to interpret fragmented snapshots of a much larger hidden acoustic network. The gaps and inconsistencies amplify the sense of a deliberate withholding, as though the Arctic itself guards its sonic secrets, refusing to allow complete comprehension. Those tracking the phenomena describe the experience as hearing fragments of a conversation in a language one cannot understand, with crucial pieces always missing. The intermittent nature of the hum conveys intention without context, creating a haunting impression of presence and awareness. Observers report a sense of pattern recognition that never resolves into comprehension, as if the environment teases the human mind with partial knowledge. This auditory teasing shapes the perception of the Arctic as a realm both alive and aloof, capable of transmitting signals yet impervious to understanding, a place where presence can be sensed but never fully mapped. These anomalies complicate under-ice expeditions, as sonar and navigation systems cannot interpret or predict the behavior of the vibrations. Vehicles relying on acoustic guidance sometimes fail to respond correctly to the low-frequency interference, introducing hazards and uncertainties. Mission planners are forced to incorporate margins of error far beyond those dictated by physical obstacles alone. In effect, the invisible hum becomes a navigational and cognitive barrier, an unseen element that restricts exploration while remaining entirely intangible, influencing decisions in ways that defy quantification. Teams exploring different methods, adjusting sensitivity, changing array layouts, cross-referencing environmental data, still find the sounds remain enigmatic. Advanced analysis offers some insight into frequency distribution and propagation patterns, yet nothing explains the origins or purpose of the emissions. Every methodological refinement produces new questions. What is producing these vibrations? Why do they behave inconsistently? And what might exist beyond the limits of detection? Each partial observation reinforces the Arctic's refusal to fully reveal its inner workings, reminding observers that some forces operate outside the realm of comprehension. Every unexplained pulse reinforces the idea that some aspect of the Arctic's under-ice environment exists beyond the reach of current understanding. The low-frequency phenomena persist across decades of observation, immune to the tools and techniques designed to map them. Even as technology evolves, the Arctic maintains a layer of auditory secrecy, reminding observers that human perception is incomplete. The persistence of these signals ensures that exploration beneath the ice remains a blend of discovery and enduring uncertainty, a challenge that transcends instrumentation and ambition alike. The persistent hum transforms the Arctic into a realm that speaks only partially, leaving humans aware of presence yet denied comprehension. The low-frequency waves act like a veil, revealing the vastness and complexity of the under-ice environment, while simultaneously keeping its source concealed. For those studying the phenomenon, the experience is unsettling, offering both evidence of something extraordinary and constant proof that much of the Arctic cannot be known through conventional means. The environment, it seems, communicates selectively, sharing fragments while withholding the whole, and every recorded pulse hints at stories still untold. The Arctic hums in a language no one has learned, and its message remains beyond reach. Magnetic instability at the top of the world. Compasses spin erratically in the Arctic, their needles twitching as if resisting any attempt to find true north. Even the most basic navigation tools fail in the region surrounding the pole, producing results that shift from hour to hour. Mariners and scientists alike report the disorienting sensation that the landscape itself refuses direction. Instruments designed for precision wobble, flicker, or freeze entirely, forcing crews to rely on intuition, celestial observation, or rudimentary calculations. Despite technological advancements, the magnetic field in this region remains capricious, a force that challenges every assumption about orientation and threatens the very notion of reliable exploration beneath the drifting ice. Instruments aboard icebreakers report sudden deviations, creating a sense of unease among crews who rely on predictable navigation. Radar and gyroscopic equipment occasionally align, only to contradict one another minutes later, as if the Arctic conspires to scramble coordinates. Mission logs describe tension growing silently, a subtle anxiety amplified by every unexplained anomaly. Even the most experienced captains speak of moments when conventional measures collapse, leaving them uncertain whether the instruments, the ice, or something unseen governs the terrain. The unpredictability forces teams into hypervigilance, their trust in technology undermined by a magnetic field that oscillates without pattern or warning. Early 20th century explorers documented mysterious shifts in compass readings that seem to defy natural explanation. Accounts from polar expeditions recount moments when bearings would swing wildly while their maps remained unchanged, and longitudes that should have held steady danced across pages. These historical observations suggest that the North Pole's magnetic quirks are not a product of modern instrumentation, but a persistent natural phenomenon that predates human measurement. Written records describe sudden reversals and inexplicable variations, hinting at an unseen, invisible architecture beneath the ice, one that humbles even the most careful observer. Satellite measurements reveal localized zones where the geomagnetic field bends and fluctuates without warning. Data from magnetometers indicate abrupt changes over distances of mere kilometers, producing anomalies that seem concentrated in narrow corridors. The irregularity confounds predictive modeling, preventing clear delineation of safe navigation paths. These zones do not follow any apparent topographical or geological logic. Mountains, ice thickness, and known subglacial structures provide no explanation. The Arctic's magnetism exhibits its own internal geometry, independent of the human understanding of poles and lines, as if an invisible hand were shaping the rules for travelers below. Subglacial geological formations interact with magnetic lines, producing irregularities that confound simple mapping. Basal rock compositions, fault lines, and ancient ridges beneath the ice influence local magnetic intensity, creating pockets of interference that warp readings. Even when researchers account for rock magnetization and geomorphology, anomalies persist, suggesting the existence of factors yet undetected. The relationship between the Arctic's physical underlayer and its magnetic signature remains partially understood, but the resulting instability acts like a hidden maze, one that challenges every instrument designed to penetrate its secrets. Navigation becomes not a matter of skill alone, but of patience in deciphering the unpredictable. Readings often swing in both intensity and direction, changing in ways that leave observers questioning the reliability of their instruments. A single compass can trace a straight line one moment and deviate drastically the next, without any discernible cause. Magnetometers fluctuate, producing peaks and troughs that contradict previous patterns. Even advanced digital systems, calibrated to the highest standards, report conflicting data. The Arctic field, it seems, possesses its own internal logic, responding to unseen currents, sub-ice anomalies, or possibly shifts in the geomagnetic pole itself. Explorers must constantly cross-check instruments, yet the more data they gather, the more uncertain the picture becomes. Electromagnetic interference occasionally disrupts sonar and communication equipment, producing silent corridors in areas thought to be fully mapped. Acoustic waves propagate irregularly, refracted or absorbed by magnetic anomalies, leaving vehicles and crews in temporary isolation. Instruments designed to navigate by echo return incomplete or misleading signals. Signals sometimes vanish entirely, only to reappear in altered form at the same location minutes later. These interruptions are more than mere technical inconveniences. They are tangible demonstrations that the Arctic's invisible forces are active participants, shaping and sometimes thwarting human perception in subtle yet undeniable ways. Mapping these anomalies with precision repeatedly falls short, revealing a field more capricious than any model can predict. Efforts to produce high-resolution magnetic maps often yield inconsistent results. Grid measurements reveal contradictions when repeated under identical conditions. The most sophisticated computational models cannot anticipate sudden deviations, and attempts to reconcile historical data with contemporary readings frequently produce further ambiguity. The Arctic's magnetism behaves like a living system, resistant to human order, and though vast arrays of instruments attempt to capture it, The result is always partial, fragmentary, and disconcerting. Shifting ice flows and hidden topography appear to influence local magnetic distortions, complicating attempts to understand their behaviour. As glaciers move, subglacial valleys and ridges beneath them alter magnetic field lines, creating transient patterns of distortion. Ice cores reveal geological histories that hint at complex interactions between the polar crust and the field above, yet modern expeditions cannot predict their real-time effects. Even slow, seemingly imperceptible ice movement produces measurable fluctuations, underscoring how interconnected the Arctic's surface, subsurface, and magnetic behaviour truly are. Explorers find themselves negotiating a force that responds to subtle shifts in ways instruments cannot fully track. Unknown sub-ice formations could be bending the field in ways not yet documented, leaving investigators puzzled. Seismic studies hint at anomalies that defy classification, potentially impacting local magnetism. Despite detailed mapping of known ridges, faults, and basins, certain regions continue to exhibit unpredictable flux. The possibility of undiscovered formations adds a layer of mystery, suggesting that beneath the ice lies a hidden architecture with the power to distort, redirect, or even shield portions of the magnetic field. Every expedition uncovers fragments of the puzzle, yet the full picture remains frustratingly beyond reach. Observed variations unfold over days, weeks, and decades, emphasizing the temporal complexity of Arctic magnetism. Longitudinal studies indicate that the field is not static. Subtle shifts accumulate, producing variations that may only become visible over months. Seasonal changes, solar storms, and variations in the ionosphere interact in ways that amplify or obscure these shifts. Tracking the field requires patience and a long view, yet even then, anomalies appear unexpectedly. This temporality transforms the Arctic from a mere geographic region into a dynamic and unpredictable force, one whose behaviour continues to evade comprehensive documentation. Even instruments placed side by side report conflicting data, leaving navigators with only partial truths to guide their path. Compass readings diverge despite identical calibration, and magnetometers operating within a few meters of one another record different intensities. Attempts to reconcile these discrepancies produce more questions than answers. The inconsistency is not a sign of malfunction, but a reflection of the Arctic's own instability. Human reliance on measurement collides with the environment's refusal to conform, creating a persistent tension between observation and reality that cannot be fully resolved. The combined effect of these instabilities creates a subtle, almost imperceptible force that shapes how humans interact with the frozen environment. Teams navigating the ice become hyper-aware of every twitch in their instruments, every unexpected shift in direction. The sensation is not merely technical but psychological, as though the magnetic field exerts a silent influence on decision-making and perception. The Arctic, in this sense, is not inert. It is an active participant, a force that challenges authority, redefines expectations, and ensures that each expedition proceeds under a shadow of uncertainty. Each measurement reinforces the impression that the Arctic's magnetic field is a barrier, an invisible boundary that resists certainty. Even with satellite assistance, sonar support, and advanced instrumentation, explorers confront a reality that cannot be fully quantified or anticipated. The field appears to curve, twist, and surge at will, producing corridors of confusion that defy mapping. Every attempt to impose structure, order, or comprehension is met with subtle contradiction, leaving the impression of a domain both navigable and unknowable, a topography defined by invisible forces rather than ice or rock. At the top of the world, the compass wavers, and the Arctic's invisible grip defies every attempt to chart its secrets. The map that remains incomplete. Vast stretches of the Arctic remain absent from every modern chart, their contours suggested only by conjecture and fragmented data. Even with decades of technological advancement, the region defies complete representation. Ice ridges, subglacial valleys, and hidden channels appear partially in satellite scans, but vanish under closer scrutiny, leaving cartographers with outlines that are provisional at best. Each map, regardless of sophistication, contains a silent acknowledgement of what is unknown, and every line drawn seems tentative, a suggestion rather than a declaration. The pole itself resists definition, a territory both measured and mysterious, where absence carries as much weight as presence. Early cartographers sketched the pole with bold lines and wide blank spaces, leaving gaps that still haunt contemporary mapping. Explorers' journals from the late 19th and early 20th centuries record uncertainty, noting entire regions of ice and sea that were impossible to chart. The audacity of early maps was matched by their incompleteness. Entire latitudes were represented by dashes or left blank. These omissions were not oversights, but reflections of the Arctic's intransigence. Even now, modern surveys echo this pattern, suggesting that the region's hidden topography has long resisted capture, as if deliberately withholding itself from human comprehension. Satellite imagery and ice-penetrating radar have illuminated portions of the under-ice world, yet much remains veiled in uncertainty. Technological breakthroughs provide glimpses into the polar abyss, revealing ridges, depressions, and pockets of water trapped beneath kilometers of ice. Still, these tools offer snapshots rather than complete narratives. Datasets are incomplete or partially obscured by ice movement and electromagnetic interference. For every ridge charted, new anomalies appear nearby. For every basin revealed, the surrounding terrain resists exact measurement. Even the most advanced instrumentation yields only fragments, leaving an impression of vast unmapped wilderness beneath the frozen surface. Survey missions often return datasets that contradict one another, producing maps that feel provisional rather than definitive. Teams working with identical instruments on similar routes sometimes report differing depths or topographical features. Small variations in timing, ice density, or environmental conditions create discrepancies that accumulate across surveys. Reconciling these differences is a painstaking process, one that rarely results in a fully coherent representation. The Arctic thus remains a patchwork of interpretations, a space where certainty is provisional and each new measurement adds both insight and confusion to the enduring mystery. Deep valleys and submerged ridges defy precise measurement, revealing only shadows of their true form beneath shifting ice. Sonar and radar can detect features, but the resolution is never absolute, and subtle anomalies escape capture. These formations influence local ice flow and water currents, yet remain largely undefined on any map. Even repeated scans over time produce partial visibility, hinting at complexity without fully revealing it. Each valley, each ridge, becomes a suggestion of structure rather than a confirmation. The Arctic's subsurface exists in a state of liminality, partially apprehended yet always eluding complete representation. Topographic models sometimes smooth over anomalies, unintentionally erasing the subtle features that make the region unpredictable. Computational methods interpolate missing data, producing visually coherent maps that conceal irregularities. Peaks, depressions, and unexpected fissures are flattened or generalized, leaving the maps more readable but less true. This act of smoothing creates a paradox. Maps become easier to use for navigation yet lose fidelity to the landscape they attempt to represent. The resulting charts are simultaneously authoritative and incomplete, embodying both human aspiration and the Arctic's enduring resistance to complete understanding. Blank spaces on maps exert a psychological weight, a silent reminder of the Arctic's enduring elusiveness. Observers are drawn to the voids, curious about what lies within them, aware that these uncharted regions may conceal hidden channels, subglacial lakes, or ridges that defy prediction. The emptiness suggests danger as much as mystery, fostering both fascination and caution. These voids are not mere absences, but active components of the map's narrative, shaping the perception of explorers and researchers who must navigate uncertainty with limited guidance. The unseen becomes as compelling as the seen, forming a backdrop of tension across every survey. Constantly moving ice undermines any notion of permanence, rendering fixed representations fleeting at best. Glacial flows shift the terrain beneath, altering apparent ridges, channels, and depressions over seasons and decades. Ice thickness changes, subglacial streams carve new paths, and previously mapped features may vanish or emerge elsewhere. Maps become provisional snapshots rather than permanent records, capturing conditions in a single moment that are already changing. The Arctic, in this sense, resists the human desire for stasis, offering only fleeting clarity before dissolving again into uncertainty. explorers planning under ice missions must navigate uncertainty, relying on partial maps that conceal as much as they reveal. Even advanced sonar and radar cannot fully account for gaps, nor predict the sudden emergence of subglacial obstacles. Decisions must be made with incomplete information, relying on probability, experience, and a keen awareness of the unknown. Each expedition is an engagement with both ice and absence, a negotiation between human intention and the Arctic's refusal to yield its secrets. The map serves as a guide, but its authority is fragile, and its blank spaces loom as silent threats. Surface features mislead as often as they guide, hiding the true configuration of the terrain below. Mountains, ice ridges, and crevasses suggest continuity where there is none, while sub-ice valleys remain invisible to the eye in most instruments. Reliance on visual cues can be deceptive, luring explorers into overconfidence before the terrain asserts its hidden complexity. Cartography must therefore reconcile two realities, the observable surface and the unseen underworld beneath, a task complicated by movement, melting, and unknown subglacial formations. Maps cannot tell the full story, and those who trust them entirely risk miscalculation. International mapping efforts reveal inconsistencies, with borders of knowledge drawn differently depending on methodology or perspective. Different nations and research teams apply varying survey techniques, each producing slightly divergent representations of the same area. No single map can claim total authority, and cross-referencing reveals disagreements in depths, alignments, and even the presence of certain features. The result is a collection of maps that overlap imperfectly, each one both illuminating and concealing, emphasizing the Arctic's resistance to universal comprehension. Filling one gap often exposes another, an unending cycle of knowledge and absence that mirrors the Arctic itself. Each new survey completes a fragment while simultaneously revealing uncharted corridors adjacent to it. Understanding seems cumulative yet incomplete, progress measured in patches and suggestions rather than comprehensive coverage. Explorers experience the paradox of discovery, uncovering new detail while confronting fresh unknowns. The map grows in scope but not in finality, leaving human understanding forever provisional, always chasing a horizon that recedes with every expedition. The map functions as both guide and enigma, a testament to human curiosity constrained by the region's mysteries. Lines drawn on paper or rendered digitally provide orientation, yet they simultaneously underscore what remains invisible. Maps inspire confidence even as they provoke doubt. They allow travel while hinting at hazards that may lie beyond perception. The Arctic becomes a domain defined by the interplay between revelation and concealment, where the representation is inseparable from the unknown. To follow a map is to acknowledge both guidance and uncertainty, to navigate a terrain that insists on remaining partly secret. Every new contour line seems to invite further questions, suggesting that no chart will ever fully capture the pole's hidden depths. As soon as one ridge is detailed, a nearby valley emerges with ambiguous form. As a lake is mapped, subglacial channels hint at pathways yet undetected. Knowledge and mystery coexist in each survey, reinforcing the sense that the Arctic will always outpace human attempts at documentation. The map, comprehensive as it appears, remains incomplete, a reflection of ambition restrained by the region's silent, unyielding will. Even advanced multispectral satellites struggle to detect subtle variations in ice composition that hint at hidden subglacial features. Differences in snow density, brine pockets, or the layering of frozen meltwater can create patterns that appear and disappear across successive images, leaving analysts unsure which details are real and which are optical illusions. These ephemeral signals suggest the presence of channels, depressions, or even shallow subglacial lakes, yet no observation has been definitive. Each fleeting anomaly reinforces the sense that the pole is not only unmapped, but actively concealing its inner structure, a place where technological eyes glimpse hints of reality without ever fully seeing it. And yet, for all the lines drawn and data collected, the Arctic refuses to be fully contained within the map's borders. Methane plumes from uncertain depths. Invisible columns of gas rise from beneath the Arctic ice, their origins unknown and their patterns unpredictable. Surveys have detected plumes that pierce kilometers of frozen ocean, escaping from subglacial sediments that remain largely unexplored. These emissions, though invisible to the eye, reveal themselves through subtle disturbances in water and ice, leaving traces that suggest both power and fragility. Scientists have observed sudden bursts that ripple across the surface, yet the precise mechanisms driving these releases remain unclear. The Arctic, in this sense, is a domain of hidden movement, where unseen chemical forces complicate every attempt at direct exploration. Subtle fluctuations in water movement and ice density betray the presence of methane escaping from sediment below. Acoustic monitors pick up faint anomalies, while temperature and salinity measurements register abrupt shifts. Patterns appear sporadic, sometimes persisting for hours, sometimes vanishing without warning. The gas itself is buoyant and volatile, rising through channels carved over millennia, yet its trajectory is influenced by ice thickness, water currents, and pressure gradients. Each detection provides a glimpse into processes otherwise concealed, revealing an Arctic world in motion, a landscape defined as much by invisible forces as by rock and ice. Some emissions are constant, others erupt suddenly, creating turbulence that challenges both measurement and understanding. Remote-operated vehicles report bubbles emerging in clusters, disturbing the surrounding water column and occasionally fracturing overlying ice. These sudden releases are unpredictable, with no discernible correlation to map topography or known subglacial features. For engineers and explorers, this unpredictability introduces a hidden risk, one that can compromise delicate instruments or endanger missions planned on the assumption of stability. Methane plumes are, in essence, both markers of life-sustaining geologic processes and agents of uncertainty, reminding all who study the Arctic that control is an illusion. Under immense pressure and sub-zero temperatures, methane behaves in ways that defy straightforward prediction or control. The frozen ice sheet acts as both barrier and conduit, regulating the flow of gas while storing immense reservoirs of energy. When trapped beneath sediments, methane forms hydrates, solid crystalline structures that dissolve under slight changes in pressure or temperature. A small shift, a subtle warming, can destabilize a region, releasing gas with explosive force. The Arctic thus contains a latent volatility, chemical energy stored for centuries, waiting to interact with the environment in ways that human understanding can only partially anticipate. Sediments beneath the glaciers hold vast stores of frozen methane, their stability fragile and often uncertain. Layers accumulated over thousands of years lock gas into compacted silts and clays, forming pockets of potential eruption. Geophysical surveys reveal domed structures and depressions that could channel emissions unpredictably, yet their precise layout remains speculative. Even minor ice flow changes may disturb these reservoirs, allowing gas to escape along unseen paths. The Arctic's under-ice sediments are both archive and threat, recording millennia of climatic change while hiding volatile reservoirs that complicate every exploration attempt. Plumes can compromise equipment or create hazardous conditions for submersibles, their effects invisible until encountered. Vehicles navigating beneath the ice may encounter sudden buoyancy shifts, bubbles that lift or destabilize instruments, or micro-explosions that crack surrounding ice. Engineers cannot fully model these forces in advance. The unpredictability of plume behavior makes safety calculations approximate. Methane becomes an invisible adversary, capable of frustrating even the most carefully prepared missions. For all the technological sophistication applied to Arctic exploration, the plumes remain a reminder that nature can assert itself beyond the reach of human design. The scientific community struggles to anticipate when or where these emissions will surface, a reminder of the Arctic's volatility. Even with years of monitoring, models can only suggest probabilities, not certainties. Patterns emerge only in hindsight, as past plume activity hints at potential hotspots rather than guarantees. Predictive algorithms attempt to correlate gas release with ice flow, temperature, and sediment composition, but the results are partial at best. Researchers acknowledge that each expedition confronts a living system, a dynamic environment that conceals more than it reveals and challenges any attempt to map or control it fully. Gas rising from below sometimes warps the ice above, leaving subtle ridges or shifts detectable only through acoustic or radar surveys. These deformations are fleeting, disappearing as the ice adjusts or melts seasonally, leaving only indirect evidence of their passage. Detecting them requires patience, repeated observation, and an interpretive eye attuned to nuance. Every ridge, bubble trace, or acoustic distortion carries information, yet never the complete story. The Arctic communicates in fragments, with methane plumes as one of its most enigmatic voices, hinting at processes that cannot be observed directly and that continue to frustrate attempts at full comprehension. Regions of recurring plume activity show no clear correlation with mapped geological features, deepening the mystery. Areas of sediment collapse, subglacial basins, or ice ridges do not consistently predict emissions. Repeated surveys reveal some locations emitting regularly, while neighbouring regions remain silent. This randomness complicates mission planning, making under-ice navigation inherently risky. The plumes defy neat categorization, existing as both observable events and elusive mysteries. Each occurrence raises questions about the Arctic's hidden infrastructure, hinting at networks of channels, fractures, and reservoirs invisible to human instruments yet active and potent. Historical expedition records hint at anomalies that may have been early observations of these elusive emissions. Logs describe unexpected currents, ice disruptions, and unusual water discoloration that modern analysis now interprets as probable methane activity. Though undocumented or misinterpreted at the time, these glimpses underscore the long-standing mystery of sub-ice gas releases. Explorers centuries ago may have witnessed the same forces that now challenge scientists, their experiences recorded only in ambiguous cryptic notes. The past thus mirrors the present, revealing continuity in the Arctic's secretive processes and the persistent difficulty of fully understanding them. Monitoring across nations is fragmentary, with overlapping surveys unable to produce a coherent picture of plume distribution. Data from satellites, submersibles, and ice-penetrating radar are collected under differing methodologies, creating gaps and inconsistencies. International collaboration improves coverage, but cannot fully overcome the Arctic's vastness and the sporadic nature of emissions. Each new observation must be interpreted in context, yet the broader picture remains incomplete. The Arctic's methane reservoirs continue to reveal themselves selectively, like a language only partially understood, leaving explorers and researchers to piece together fragments into an ever-evolving mosaic. The uncertainty of emissions dictates cautious planning, forcing every under-ice operation to contend with potential instability. Mission parameters must include contingency for sudden turbulence or gas release, and engineers design vehicles with redundancy and resilience. Even with such precautions, no approach eliminates risk entirely. The presence of methane plumes transforms under-ice exploration from a technical challenge into a negotiation with an invisible and volatile natural system. Each step forward depends on both careful calculation and acceptance of unpredictability, underscoring the Arctic's role as a domain beyond human control. Methane serves as a silent intermediary between unseen geologic activity and the frozen surface, revealing presence only indirectly. Its release communicates the state of subglacial sediments, ice stability, and thermal dynamics, yet always in a partial, fragmented manner. Researchers interpret chemical signatures, acoustic disturbances, and subtle ice shifts to reconstruct the story of what lies below. The Arctic's chemical signals are like whispers, incomplete but compelling, urging caution and respect. Methane plumes exemplify the unseen forces shaping the region, a reminder that exploration is as much about interpreting silence as observing substance. The Arctic's hidden processes remain beyond direct observation, rising and vanishing in ways that resist human comprehension. Each plume is a fleeting event, a pulse of gas that connects deep geological time with the present, visible only through its subtle interactions with water and ice. Despite decades of study, the patterns remain elusive, the mechanisms only partially understood, and the consequences uncertain. Methane is both marker and messenger, a sign of activity that cannot be fully controlled, charted, or predicted, leaving every expedition to contend with the Arctic's capricious and invisible dynamics. Somewhere below the ice, the plumes rise and vanish, a hidden pulse of the Arctic that refuses to be tamed. Seismic tremors in a supposedly quiet basin. A subtle vibration pulses through the Arctic basin, imperceptible to the eye yet recorded by sensitive seismographs. The region has long been considered geologically stable, a quiet expanse beneath kilometers of ice where little movement was expected. Yet careful instrumentation has revealed faint quivers, intermittent pulses of energy that traverse the frozen ocean floor. These tremors, often unnoticed by casual observation, hint at hidden processes operating beneath a seemingly inert surface. For explorers and scientists, their presence transforms the Arctic from a static environment into one that is quietly restless, its stillness punctuated by invisible motion, whispering of forces humanity barely comprehends. Sensors beneath the ice detect faint energy waves, moving unpredictably across the ocean bed. The vibrations register as minute deflections in seismometers, their frequency and amplitude varying in ways that resist simple explanation. Unlike earthquakes, these tremors are subtle, sometimes lasting mere seconds, sometimes persisting for minutes, yet always leaving detectable traces. Acoustic instruments also record micro-resonances in the ice, indicating a dynamic interaction between the frozen surface and the shifting sediments below. Each reading suggests that the basin is alive in ways invisible to the eye, a network of mechanical energy concealed beneath layers of ice and water that continues largely undisturbed. Occasionally, tremors ripple outward, altering the pressure and tension of overlying glaciers without warning. Subglacial ice can respond to these disturbances with microfractures, tiny shifts that accumulate imperceptibly over time. Even massive ice sheets, previously thought immovable on human timescales, reveal sensitivity to the forces below. These interactions are difficult to predict, and small events can cascade, subtly influencing the stability of the surface. Explorers must contend with this unseen variability, aware that beneath their feet or beneath the hulls of their submersibles, the Arctic is not the quiet, controllable landscape it appears to be, but an environment that conceals restless, unpredictable power. Ice ridges shift slightly in response, leaving patterns that appear almost deliberate, yet are entirely natural. A series of linear fractures or raised edges may mark where energy has been transferred from the seabed to the frozen surface. The effects are so subtle that they are often misinterpreted as wind-driven deformation or seasonal ice movement. Only careful measurement over time reveals the connection to seismic activity below. These hidden shifts serve as visual clues to otherwise undetectable forces, whispering the Arctic's secrets to those patient enough to read them, revealing a system that is far from inert. Subsurface rock formations creak and compress, a reminder of the Arctic's hidden dynamism. Fault lines, sedimentary layers, and compacted glacial deposits respond to stress, storing energy that can be released intermittently as tremors. This subterranean motion is rarely violent, but it is persistent, a continuous reshaping of the frozen underworld. Geologists interpret these signals as evidence that even the coldest, most remote basins are subject to deep geophysical processes, hinting at a complexity of motion that remains largely uncharted. Each tremor, however minor, serves as a testament to the Arctic's unseen restlessness, a force that shapes both the land and the ice above in subtle, continuous ways. Even the calmest stretches of ice are not immune to these minute shocks, which travel unseen for kilometers. Energy can propagate through the water column and the ice itself, producing pressure changes that are felt far from the source. Submersibles and research stations must account for this invisible motion, which can shift instruments or disturb delicate measurements. The tremors demonstrate that stability in the Arctic is relative, contingent on what is unseen below the surface. For those mapping or exploring the region, the presence of these subtle forces is both a puzzle and a persistent hazard, challenging all assumptions about the Arctic's placidity. Models that once depicted the basin as stable are now challenged by sporadic seismic signals. Early maps treated the Arctic floor as static, relying on indirect observations and assumptions of minimal tectonic activity. Modern instrumentation has revealed that this assumption is incomplete. Tremors are neither rare nor entirely random. Each recorded pulse challenges prior conceptions and demands a re-evaluation of geological risk. The basin, once imagined as placid and predictable, emerges as a domain of hidden energy, where unseen forces interact with ice, water, and sediment in complex and largely unpredictable ways, defying simple interpretation. Historical measurements hint at irregular pulses, suggesting that previous expeditions may have sensed tremors unknowingly. Logs from mid-20th century Arctic voyages occasionally mention unexplained vibrations, unexpected shifts in submersible depth, or subtle water column disturbances. At the time, these observations were often dismissed as mechanical error or natural variability. In retrospect, they may represent some of the earliest evidence of the tremors now recorded systematically. Such historical glimpses underscore the continuity of the Arctic's hidden processes and the persistent challenge of interpreting signals from a world largely concealed beneath ice, where even small anomalies carry weighty significance. Coordination among international monitoring stations reveals overlapping zones of subtle activity, yet no complete map exists. Nations share data from seismic arrays, sub-ice acoustic monitors, and satellite observations, yet coverage remains patchy. Some areas are densely monitored, while vast stretches go unobserved. Consequently, tremors are understood in fragments, each station capturing only a partial view of a broader dynamic system. The Arctic's secrets are revealed selectively, leaving researchers to piece together incomplete mosaics and to anticipate movement in regions where direct observation remains impossible, reinforcing a sense of constant uncertainty. Seasonal ice movements sometimes coincide with heightened tremor frequency, hinting at complex layered interactions. Melting, refreezing and shifting ice can alter pressure on the seabed, amplifying or dampening underlying seismic activity. Conversely, tremors can accelerate ice deformation, producing feedback loops that further complicate modelling efforts. These interactions reveal the Arctic as a system in constant negotiation between ice, water and rock, a multi-layered environment where stability is relative, fleeting and unpredictable. The interplay of forces emphasises why exploration beneath the glaciers remains fraught with uncertainty, a challenge both technical and existential. Engineers planning subglacial missions must consider the sudden, invisible force of these vibrations. Vehicles designed for ice penetration or under ice navigation require careful calibration to withstand unexpected jolts or shifts. Even minor tremors can alter buoyancy, pressure distribution, or structural stress, creating operational hazards. Designing for such variability challenges both imagination and technical skill, forcing mission planners to incorporate contingencies for the unknown. Tremors are thus both scientific phenomena and practical obstacles, shaping not only understanding but also the feasibility of human activity beneath the ice, where one miscalculation could have consequences amplified by the environment's concealed forces. Debate persists over the origins of the tremors, with hypotheses ranging from tectonic stress to subglacial water shifts. Some suggest that glacial movement alone could generate sufficient stress to produce detectable pulses. Others propose that sediment compaction or cryoseismic activity may play a role. No single explanation accounts for all observations, and the interaction of multiple factors is likely. This uncertainty contributes to the Arctic's aura of mystery, a region whose apparent serenity belies the ongoing, unseen forces shaping its hidden depths, keeping every expedition cautiously tentative. The basin conceals a network of invisible stress points, each capable of releasing energy that humans can neither predict nor control. Microfractures, fault intersections, and sediment anomalies create a patchwork of potential activity, with energy transferring subtly from point to point. Even in areas considered low risk, tremors can manifest unexpectedly, reminding explorers that safety in the Arctic is provisional. Every expedition must contend with these hidden vulnerabilities, acknowledging that beneath the ice lies a restless mechanical pulse that defies observation and challenges comprehension, a quiet menace beneath the apparent calm. Awareness of this restless underworld adds a quiet urgency to every Arctic expedition, a silent reminder of forces beneath the ice. While surface conditions may appear placid, the basin's tremors influence navigation, equipment safety, and scientific interpretation. Every decision, where to drill, where to send a submersible, how to schedule a survey, must account for these unseen forces. The Arctic emerges not as a passive environment but as a participant in exploration, its hidden movements shaping human understanding as much as any instrument or observation, a reminder that control is always partial. Below the seemingly still surface, the basin shivers in secret, a restless heart of the Arctic yet to be understood. The drift station's unresolved reports. In the years following the Second World War, the Soviet Union established a network of drifting ice stations across the Arctic Ocean, designed to monitor atmospheric conditions, ocean currents and ice movement. These stations, often little more than wooden huts mounted on floating ice floes, became the first prolonged human presence atop the Arctic cap. Among their meticulously logged observations were strange vibrations and cracking noises beneath the ice, phenomena that did not conform to known ice dynamics. Reports of these events sent sporadically by radio hinted at forces operating in the under-ice environment that remained wholly unexplained, casting a shadow over any attempt to penetrate the region further. The early records, some of which have since been declassified, describe the station's instruments registering tremors that resembled miniature earthquakes, yet occurred in the middle of seemingly solid ice sheets. Station personnel, often working under isolation and extreme conditions, reported the ice groaning and shifting with sudden intensity, accompanied by low-frequency sounds that instruments could detect, but the human ear could barely perceive. The peculiar timing of these vibrations, sometimes synchronized with ocean swell, sometimes entirely independent, suggested forces at work beneath the frozen surface that were beyond the immediate understanding of contemporary glaciologists. Detailed logs from Station North Pole 2, deployed in 1951, contain accounts of ice fracturing in patterns that could not be explained by temperature fluctuations or wind stress. One entry records a section of the floe suddenly heaving upward, lifting equipment and leaving deep fissures behind. While minor cracks were expected, the scale and rapidity of these movements were not consistent with known ice physics, and no nearby seismic activity was reported that could account for the observations. Such anomalies, while systematically documented, were never resolved in a way that would clarify the underlying cause or predict future occurrences. The psychological impact on drift station crews was notable, with some observers writing of an unsettling hum beneath their feet during periods of intense cracking. The hum appeared to originate from deep within the ice or possibly the water below, creating vibrations that permeated living quarters. Despite attempts to measure these disturbances with the equipment available at the time, the recordings were inconclusive, leaving the sensations largely anecdotal yet persistent in multiple stations. These accounts, when reviewed decades later, underscored the difficulty of interpreting under-ice phenomena from surface observations alone. Soviet engineers attempted to quantify the stress patterns by embedding early strain gauges into the ice, hoping to chart the movement of flows in relation to temperature and current. These gauges captured rapid fluctuations that defied expected trends, including abrupt compressions and shifts in sections of ice hundreds of meters across. Though some of the data were later incorporated into broader studies of sea ice mechanics, many files remain incomplete or redacted, creating gaps in the historical record. The anomalies, when placed alongside human reports, pointed to an Arctic underworld that was physically active yet nearly impossible to study directly. The stations themselves were vulnerable to the capricious nature of the ice. Several were abandoned when cracks widened or flows began to break apart, sometimes taking critical equipment with them into the depths of the ocean. This meant that not only were the phenomena under-recorded, but the destruction of platforms also severed continuity in data collection, leaving a patchwork of incomplete observations. Efforts to reconstruct these events relied on sparse logs, scattered photographs, and occasional recovered instrumentation, each fragment contributing to a growing sense of under-ice mystery that no single expedition had yet resolved. Attempts to triangulate the sources of the vibrations faced inherent limitations. The drift stations were widely spaced and constantly moving with the ice, creating an ever-shifting observational network. Signals captured at one station could not be reliably cross-referenced with another, and temporal discrepancies in reporting made correlating events nearly impossible. The resulting maps of activity were incomplete, displaying only the faint outlines of irregular tremors and unidentifiable shifts. For contemporary scientists, these limitations underscored the logistical impossibility of safely exploring beneath the central Arctic ice, where forces operated beyond predictable parameters. Some researchers speculated that the vibrations might be linked to under-ice water currents, tidal pressures, or even early interactions with the slowly rising Atlantic waters beneath the ice cap. While these explanations accounted for portions of the observed activity, they could not fully describe the sudden fracturing and anomalous sounds consistently reported. The persistence of unexplained events over years suggested a mechanism or set of conditions hidden beneath the ice, inaccessible to the drifting station's instruments and to human observation, creating a barrier that has yet to be overcome. In addition to mechanical and hydrological theories, the stations recorded unusual magnetic readings at times coinciding with the ice tremors. Compass deviations were occasionally reported, affecting navigation for personnel and small vehicles deployed on the ice. These disturbances were subtle yet consistent enough to raise concerns that whatever forces were causing the vibrations might also have electromagnetic consequences. Though no definitive link could be proven, the correlation reinforced the perception that the Arctic surface, while ostensibly frozen and stable, hid a complex system of interacting forces just beyond reach. Scientific teams in Moscow reviewed the reports with caution, often dismissing the most sensational claims while preserving raw data for further study. The lack of definitive explanation did not prevent speculation within internal Soviet channels. Some suggested the phenomena were evidence of previously undocumented geological structures beneath the ice. Others posited that under-ice currents carried trapped air pockets that periodically released energy in unpredictable bursts. Each theory remained unverified, and no expedition had been able to systematically investigate the source of these vibrations without risk to both personnel and equipment. Despite the many unanswered questions, the drift stations contributed to a remarkable body of observational data on the Arctic environment. Their records of temperature fluctuations, ice movement, and seasonal transitions remain invaluable. Yet, alongside these achievements, the unresolved reports of under-ice vibrations serve as a chilling reminder of the limits of human presence in the polar expanse. Every mention of sudden cracking or inexplicable hum hints at a domain where nature's forces operate on a scale and with a precision that eludes both understanding and instrumentation. Modern reanalysis of the logs using contemporary seismic and oceanographic models has confirmed that some of the reported vibrations are plausible given known ice and water dynamics. However, certain recorded events continue to defy categorization. Simulations cannot fully replicate the intensity, frequency, or sudden onset described by station personnel, leaving a residue of uncertainty. This disconnect between observable phenomena and theoretical models underscores why exploration beneath the North Pole's central ice remains a dangerous and largely speculative endeavour. The human narratives preserved in journals and letters are perhaps the most compelling evidence of the drift station's unresolved mysteries. Crews described the ice as alive, shifting with a will of its own, creating tension and anxiety that few outside the Arctic could comprehend. While framed as objective reports, the underlying sense of an unknown force operating just below the surface permeates the documentation. It is a tension not measured in meters or degrees, but in the persistent inability to understand what lies beneath the frozen expanse. Ultimately, the legacy of the drift stations is twofold. They provided the first long-term human observations of the central Arctic, yet they left as many questions unanswered as they answered. The phenomena they recorded, sudden tremors, low-frequency hums, and inexplicable fracturing, highlight the persistent barrier to direct exploration under the North Pole's glaciers. Each abandoned station and lost instrument serves as a testament to the difficulties of collecting continuous, reliable data in an environment where nature's forces remain largely opaque. Even decades later, researchers compiling the historical reports find themselves piecing together fragments of knowledge, assembling patterns that suggest activity beneath the ice that modern science cannot fully explain. The Arctic's drifting platforms were both witnesses and victims of a world inaccessible to humans, where movement, sound, and vibration persist beyond measurement. In studying these stations, one is confronted not with clear answers but with the stark realization that some regions of the planet resist observation, defy interpretation, and retain their secrets despite human persistence. Every crack and hum noted in the logs remained an unanswered question beneath the frozen surface. Submarine navigation anomalies. In the shadowed waters of the central Arctic, submarines encounter forces that instruments cannot fully track, making navigation an exercise in uncertainty. Even with nuclear-powered vessels designed for prolonged under-ice missions, crews quickly learn that charts and sonar are only partial guides. The polar cap conceals complex topography and unpredictable currents that strain both human judgment and technological systems. Early Cold War patrols revealed that submarines could traverse seemingly open channels one day, only to find the same route blocked or distorted the next, leaving officers to confront the limits of precision in a domain where mistakes could be fatal. Hulls vibrate with the faint resonance of unseen currents, and every sonar ping hints at obstacles that do not appear on any chart. Operators report strange acoustic reflections that seem to emanate from voids or ridges beyond direct measurement, creating a dissonant sense of space around the vessel. Even minor shifts in under-ice currents can bend sonar waves, producing ghost images that confuse navigation. The constant hum of machinery, combined with the low-frequency echoes of distant ice movement, forms a soundtrack of uncertainty that can unsettle the most experienced submariners, making the Arctic's submerged world feel both alive and deliberately obscure. Historical patrol logs describe compasses swinging erratically, defying the experience of navigators accustomed to polar regions. In some missions, even calibrated magnetic compasses would deviate by degrees too large to attribute to standard variation. Officers learned to cross-check instruments against inertial navigation systems and visual cues from sonar, yet anomalies persisted. These deviations were not uniform. Sometimes the same instruments performed flawlessly one day and unpredictably the next. The logs suggest that forces beneath the ice, whether geomagnetic anomalies, oceanic currents, or unknown topography, can interfere with navigation in subtle but persistent ways, leaving submarines in a state of suspended uncertainty. Ice keels and submerged ridges twist the flow of water, producing currents that push vessels off course without warning. Cold, dense currents descend from the surface, interacting with warmer, less dense water beneath, generating turbulence along underwater slopes. Submarines navigating these environments may experience sudden lateral forces, imperceptible until the vessel responds unexpectedly on instruments. Even experienced helmsmen can misjudge the impact, and course corrections sometimes amplify deviations rather than correct them. These hidden structures beneath the polar ice form an invisible lattice that channels water and energy, creating conditions no navigational chart can fully capture and no sonar can perfectly resolve. During a Cold War mission, sonar operators recorded echoes that suggested structures far larger than any known undersea formations. The shapes appeared intermittently, only on certain pings, and vanished when the vessel adjusted speed or depth. Engineers attempted to reconcile the signals with known geology, ice drafts, or man-made objects, yet the evidence persisted. Declassified fragments of these reports hint at ridges or cavities beneath the central Arctic ice, though exact dimensions and positions remain speculative. For crews at the time, such readings were more than an operational concern. They were a reminder that the North Pole's hidden environment could behave independently of any expectation. Electrical instruments occasionally registered movements that could not correspond to the submarine's actual trajectory, generating cryptic readings. Depth gauges, inertial systems, and sonar sometimes appeared to contradict each other, as if the vessel existed in multiple positions simultaneously. Investigators later proposed that complex interactions between magnetic anomalies, ice density variations, and under-ice currents could explain parts of these readings, but not all. The phenomena were intermittent and inconsistent, leaving room for speculation. Crews had to make real-time decisions without fully understanding the forces affecting them, relying on intuition as much as technology to navigate an environment that was fundamentally unknowable. Officers recount moments when depth and navigation indicators contradicted each other, creating tension that weighed on every decision. In extreme cases, a vessel would appear stable according to one set of instruments, while another suggested a slow, unseen tilt. This produced operational dilemmas. Trusting the wrong data could lead to collisions with submerged ridges, ice keels, or even other vessels. The psychological pressure of uncertainty compounded physical challenges, especially in missions lasting weeks under the Arctic cap. The logs of these experiences convey a profound unease, as if the very environment resisted being mapped or predicted, asserting its autonomy over human technology. Intermittent irregularities followed no discernible pattern, as if the Arctic currents themselves shifted according to rules unknown to science. Navigation anomalies appeared in clusters, then disappeared for weeks, frustrating analysis. Engineers and oceanographers attempted to model these shifts using bathymetric data and under-ice current simulations, but the patterns proved elusive. Some hypothesized that tidal effects, variations in ice thickness, or deep thermoclines could partially account for the anomalies, but these explanations addressed only a fraction of the recorded phenomena. The unpredictability reinforced the perception that the North Pole was not merely unexplored, but actively resistant to systematic observation beneath its surface. Contemporary simulations of under-ice hydrodynamics reproduce some anomalies, yet abrupt disturbances remain beyond precise explanation. Advances in computational modelling allow scientists to estimate water flow, ice deformation, and temperature gradients, but real-world readings continue to surprise. Submarines moving along predicted paths occasionally experience unanticipated lateral or vertical forces that simulations cannot account for. Even with modern equipment, the Arctic's concealed under-ice structures, ridges, keels, and cavities interact with vessels in ways that remain largely mysterious, preserving a level of operational uncertainty that discourages extensive exploration. Certain missions were forced to turn back when ice or sudden depth changes damaged equipment, cutting observation short. Mechanical failures, broken sonar arrays, or compromised ballast systems ended patrols prematurely. These incidents illustrate the stakes of navigating under an ice cap, where every anomaly could have cascading consequences. The combination of environmental hostility and technological limitation emphasizes why human exploration under the North Pole's glaciers has remained restricted. Even today, vessels face risks that are difficult to quantify, and many regions remain virtually unreachable. Submerged terrain, from hidden ridges to unexpected ice formations, interacts with vessels in ways that resist accurate prediction. A sonar echo may reveal a peak one moment, only for the same location to appear as empty space later. Instruments measure movement but cannot always differentiate between shifting ice above, water currents, or geomagnetic distortions below. These unknowns accumulate, producing a domain where navigation becomes part science, part intuition, and part blind trust in machinery that can fail without warning. Unlike surface stations, submarines must interpret every vibration and echo through the filter of human judgment, with no direct line of sight. Where ice stations had a visual horizon and audible cues, submarines rely entirely on instruments, sonar, and experience to navigate a dark, frozen maze. Each ping of sonar or fluctuation in the compass can be misleading, producing a fragile perception of certainty. Crews are forced to make decisions in a constantly shifting environment, aware that the Arctic conceals forces that defy immediate comprehension, and that a single miscalculation can have irreversible consequences. Even advanced sonar arrays occasionally produce conflicting data, highlighting regions where navigation becomes unreliable. In some areas, signals return distorted or fail to return at all, leaving patches of unknown terrain on maps. Engineers attempting to model these anomalies acknowledge that the ice above and the water below create complex interactions that their instruments cannot fully capture. The result is an under-ice landscape of partial knowledge, where every mapped feature comes with a margin of doubt and every decision carries a hidden risk. Reviewing decades of Arctic patrols reveals repeated moments of disorientation, hinting at a hidden environment beyond human control. Even with improved sonar, GPS-assisted surface calibration, and sophisticated modelling, the pattern of unexpected anomalies persists. Submarines document shifts, deviations, and acoustic irregularities that cannot be easily explained, forming a body of evidence that suggests a layer of the Arctic is fundamentally inaccessible. These unresolved mysteries persist as silent guardians of the polar depths, discouraging further incursions and leaving much of the region effectively unexplored. The Arctic's under-ice corridors remain a labyrinth of unpredictable currents, magnetic fluctuations, and unseen obstacles that defy human mapping. Each mission contributes fragments to a growing archive of partial understanding, yet the full picture remains tantalizingly out of reach. Navigation anomalies, though sporadic and sometimes subtle, consistently demonstrate that beneath the North Pole, forces operate beyond the limits of instruments and experience. The evidence gathered over decades conveys a persistent truth. Exploration here is as much an exercise in humility as it is in technology. In the Arctic's concealed depths, submarines trace only fragments of paths that the ice itself chooses to obscure. Satellite irregularities directly above the pole. From hundreds of kilometers above, the North Pole resists clarity, presenting satellite sensors with irregularities that challenge even the most advanced instruments. Orbital images and sensor readings often produce gaps or distortions that are impossible to reconcile, creating zones of uncertainty over the ice cap. Historical and modern analysts alike have noted that the central Arctic appears to defy continuous observation, leaving both weather forecasting and mapping incomplete. Even satellites equipped with multiple instruments experience difficulty in capturing consistent data, a persistent reminder that the polar region behaves differently than any other surveyed area on the planet. Early polar orbit satellites were designed to chart ice, weather and topography, yet their paths converged over the pole in ways that left persistent blind spots. Orbits aligned to maximize coverage inadvertently caused overlapping passes at extreme latitudes, where small timing discrepancies could leave weeks-long gaps in observation. Engineers noted that the convergence of orbital tracks, combined with the pole's rotational characteristics, created subtle but systematic data inconsistencies. For decades, these limitations went largely unaddressed, illustrating the difficulty of maintaining continuous surveillance in the region and exposing how even the most sophisticated early satellites could not fully penetrate the Arctic's frozen expanse. Analysts noticed data gaps that could not be attributed to technical failure, revealing portions of the ice cap that remain effectively unobserved. In some cases, cloud-free imagery would suddenly vanish over the same coordinates, leaving entire sectors unrecorded for days. Meteorologists and geographers studying historical archives found recurring blank areas in orbital datasets, suggesting that environmental factors or natural interference might periodically obscure the surface. These absences were not random. They indicated regions that resisted observation in a pattern that modern modelling has yet to fully explain, hinting at forces or conditions above or within the ice that deflect or distort remote sensing. Some imagery displayed unexpected distortions, areas of inexplicable brightness or shadow that refuse consistent interpretation across successive passes. Sensors calibrated for reflective snow and ice frequently returned anomalous results, where ridges, pressure ridges and melt ponds appeared exaggerated or disappeared entirely. Even advanced optical processing could not reconcile these anomalies with ground truth, leaving certain maps partially speculative. Analysts observed that while the distortions could occasionally be linked to solar reflection or auroral interference, other inconsistencies lacked any identifiable cause, suggesting that the North Pole presents an environment that defies the logic of observation. Programs such as TIROS and Landsat struggled to maintain continuous coverage, demonstrating that the highest latitudes were uniquely resistant to observation. While mid-latitude imaging was generally predictable and consistent, the poles produced persistent data irregularities, frustrating mission planners. Satellite engineers noted that signal reception, timing, and resolution were all affected by polar positioning, requiring recalibration and repeated passes to even approximate complete coverage. Despite technological advances over decades, the highest latitudes consistently revealed gaps, emphasizing the Arctic as an area where remote sensing reaches its limits. Solar glare and polar auroras often interfered with optical and infrared sensors, creating momentary lapses in data that compounded over time. Auroral displays, while spectacular to observers, scattered electromagnetic radiation in ways that corrupted sensor readings, producing distorted or missing imagery. Reflections from snow and ice created additional challenges, particularly when the sun remained near the horizon during extended polar daylight. These environmental phenomena, combined with sensor limitations, produced an unpredictable observational environment, leaving analysts with partial, intermittent snapshots of an ice cap that resisted continuous monitoring. Irregularities occurred without predictable pattern, with certain regions appearing clear one week and entirely obscured the next. Analysts attempted to identify repeatable correlations with temperature, ice drift, or solar activity, but the results were inconclusive. Data gaps persisted even in areas that appeared stable from previous images, suggesting that the North Pole is subject to transient phenomena that disrupt satellite observation. This unpredictability creates a situation where portions of the Arctic remain virtually uncharted, complicating any attempt to plan under ice expeditions or understand glacial behavior in a holistic way. These observational anomalies forced planners to treat parts of the central Arctic as effectively unmapped, complicating any attempt to chart its under-ice terrain. Expedition teams rely on remote sensing to assess ice thickness, identify hazards, and estimate navigable routes, yet inconsistent satellite data produces zones of uncertainty. Gaps in imaging translate directly into operational risk. No instrument can confirm what lies beneath, leaving researchers dependent on fragments of partial information. As a result, large areas of the North Pole remain off-limits to both surface and under-ice exploration, their secrets preserved by the limits of remote observation. Atmospheric conditions above the pole further complicate observation, with layers of ice crystals, high-altitude haze, and temperature inversions bending or scattering satellite signals unpredictably. Instruments designed to detect surface reflectivity, thermal emissions, or microwave signatures occasionally register phantom features or sudden voids, creating maps that cannot be verified on the ground. In some cases, entire stretches of the ice appear distorted, as if warped by unseen forces, leaving analysts uncertain whether the anomalies are environmental artifacts or limitations of the sensing technology itself. This interplay between the atmosphere and orbital instruments ensures that even the clearest satellite cannot render the pole entirely transparent. When compared to mid-latitude regions, satellite performance over the pole revealed a stark contrast. The Arctic remained a persistent outlier in data reliability. Sensors that perform flawlessly at lower latitudes regularly fail to produce coherent imagery over the central ice cap. Historical comparisons of Landsat, NOAA, and modern synthetic aperture satellites illustrate this pattern clearly, with the highest latitudes showing the most persistent and inexplicable gaps. Even advances in geospatial analysis and data correction cannot fully reconcile these anomalies, highlighting the North Pole as uniquely resistant to surveillance and systematic study from space. Modern radar and synthetic aperture systems improved resolution, but still encountered intermittent blind zones, emphasizing the inherent difficulty of polar surveillance. Synthetic aperture radar can penetrate cloud cover and darkness, yet even these technologies occasionally fail to render consistent imagery over ice ridges, melt ponds, or shifting flows. Engineers and researchers continue to investigate the causes of these blind spots, exploring everything from electromagnetic interference to dynamic ice morphology. Despite their sophistication, these instruments cannot eliminate uncertainty, leaving the Arctic's central ice cap partially concealed even from orbital observation. Oceanographers and climatologists attempting to reconcile overlapping datasets found contradictions that could not be fully resolved, leaving only partial insight. Maps generated from different satellites often disagree on ice thickness, coverage, or topography, forcing scientists to treat each dataset as an approximation. Statistical modelling reduces error margins, but cannot produce definitive results, creating persistent ambiguity. These unresolved contradictions reinforce the sense that the Arctic is a domain where even the most meticulous observation yields incomplete knowledge, maintaining a layer of mystery that extends from the ice's surface to the hidden under-ice environment. The gaps in orbital observation function almost like a filter, limiting human understanding and reinforcing the secrecy of the ice-covered region below. Each missing image or anomalous reading emphasizes how the environment obstructs direct observation, leaving large swaths of the North Pole effectively unknowable. Analysts often describe this as the polar paradox. The closer satellites approach the pole, the more resistant it becomes to precise measurement. The effect is cumulative, producing a persistent veil that obscures ice morphology, movement, and potential under-ice hazards, and indirectly discouraging exploratory missions beneath the glaciers. Decades of satellite imagery collectively document the Arctic as a place of fragmented knowledge, where persistent irregularities suggest unknown forces at work. Long-term analyses reveal that no single satellite system can fully cover the central ice cap without intermittent gaps, and even modern constellations must rely on interpolation to fill missing data. These limitations create a scenario in which the Arctic is perpetually only partially visible, preserving the enigma of its under-ice terrain. Repeated anomalies, inconsistent signals, and data voids reinforce the notion that certain regions are effectively hidden from human study. Reconciling technological achievement with observational failure highlights a recurring truth. The ice and its surroundings resist being fully surveyed, no matter the vantage point. Each new satellite, radar system, or imaging technique advances understanding, yet gaps persist, demonstrating the limits of human perception and engineering. the central Arctic continues to present a challenge that is both technical and environmental, where natural conditions combine with orbital constraints to obscure the ice below. These persistent irregularities are as tangible as they are frustrating, a reminder that exploration remains constrained not by imagination but by conditions beyond control. Even from orbit, the North Pole chooses what can be seen, leaving fragments of the ice and its hidden depths forever unresolved. The ice that erases the record. Entire research stations have vanished beneath shifting flows, leaving months of data and human effort erased in a matter of hours. Throughout the history of Arctic exploration, drifting ice has proven capable of dismantling carefully constructed platforms, scattering both equipment and documentation into the void. Crews who venture onto these frozen expanses do so under the constant knowledge that the very ground beneath them is unstable, unpredictable, and capable of swallowing their work whole. Each lost station represents more than a logistical setback. It is a tangible reminder of the Arctic's ability to erase traces of human presence entirely. Even the most experienced teams acknowledge that preparation can only mitigate, never eliminate the ice's capacity for destruction. Devices once recording tides, temperature, and ice thickness now lie buried or scattered across drifting ice, their readings permanently interrupted. Scientific arrays and remote sensing modules, often painstakingly installed at the edge of pressure ridges or atop ice flows, cannot withstand the constant grinding and crushing of shifting ice masses. Even temporary calm, when sensors can operate for days or weeks, is fleeting. The ice moves, flexes, and fractures unpredictably, converting months of careful observation into gaps that future scientists cannot reconstruct. Such disruptions do not merely hinder understanding, they erase the continuity required to detect long-term patterns, leaving critical environmental questions unanswered. Logs from Soviet drift stations recount platforms breaking apart mid-expedition, with crews forced to abandon not only equipment but vital observations. In some cases, personnel had only hours to evacuate floating stations before ice ridges tore through foundations, or the flows themselves disintegrated under stress. The records that survived these events often hint at phenomena never fully captured, leaving researchers reliant on fragmented notes and incomplete datasets. The stories of these stations reveal not only physical loss, but also the psychological strain on scientists who watched months of work vanish beneath moving ice, underscoring the Arctic's relentless challenge. The immense weight of frozen ridges and pressure-driven fractures has crushed fragile monitoring arrays, rendering carefully calibrated experiments meaningless. Instruments designed to measure subtle changes in ice thickness, ocean salinity, or atmospheric pressure are often smashed or rendered inoperable when flows collide. Even advanced engineering, including reinforced platforms and shock-absorbing mounts, cannot fully compensate for the immense shifting forces at work. The Arctic ice acts as both a laboratory and an adversary, testing the limits of human technology with relentless persistence. Its power is not random, but systematic, reshaping the landscape in ways that render human precision ephemeral. Sudden openings in the ice, called leads, can swallow installations in moments, separating them from personnel and disrupting months of careful monitoring. These fissures appear without warning, and in the polar night their black voids are invisible until approached too closely. A station once safely positioned may find itself stranded on a fragmenting flow, its support compromised as ice shifts beneath it. The fleeting stability of human installations is constantly challenged by these unpredictable fractures, emphasizing that the Arctic is not merely a landscape but a force that actively resists observation. Scientists have observed that even minor temperature fluctuations can accelerate the opening of leads, adding another layer of unpredictability. Long-term studies are repeatedly undermined as flows carry stations far from intended coordinates, producing gaps that ripple through climatological and oceanographic records. Drift trajectories can transport entire platforms hundreds of kilometers from their initial locations, destroying continuity in time series data. Such movements introduce unavoidable uncertainty into scientific analyses, making it impossible to know whether changes in ice thickness or ocean currents are natural or artifacts of displaced observation points. The ice, in its relentless mobility, serves as both medium and barrier, carrying knowledge away from reach and amplifying the mystery of the regions beneath its frozen surface. One documented drift saw an entire station carried out of range before it could transmit collected data, leaving a void in the scientific archive. Communication failures, compounded by remoteness and extreme weather, mean that months of painstaking data collection vanish with little trace. Researchers are often left piecing together observations from surviving fragments, attempting to reconstruct events that may never be fully understood. The loss extends beyond data. It erases the context of measurements, the spatial relationships critical to interpreting ocean currents, ice formation, and temperature gradients. The ice does not merely obstruct, it actively removes traces of human presence, erasing physical structures and recorded observations alike. Platforms, tents, and measurement arrays may disappear entirely beneath a pile of fractured ice, leaving no indication of prior occupation. Even when artifacts resurface elsewhere, they are often damaged or incomplete, providing only partial insight into prior operations. In this sense, the ice functions as both a destroyer and a curator, controlling the preservation of knowledge according to forces beyond human influence. Its selective destruction of material evidence ensures that certain regions remain almost entirely unknowable. Even reinforced or mobile platforms succumb eventually, a reminder that no design can fully resist the Arctic's shifting authority. Engineers have constructed floating bases, modular arrays, and specialized anchors, yet each innovation eventually meets its limit against the sheer pressure of moving ice. Lessons learned from one station may inform the design of another, but the inevitability of loss remains a constant. The Arctic's movements operate on a timescale both patient and brutal, erasing human constructs long before they can become permanent fixtures in the environment. Submarine and under-ice missions dependent on surface support are disrupted when supply stations vanish, forcing abrupt course changes or mission cancellations. Icebreakers, resupply crews, and communication relays rely on known positions of surface stations, and when these are lost, missions must be altered or aborted. The unpredictability of drifting ice thus extends beyond observation, affecting exploration planning and even safety, demonstrating that the Arctic's erasure of human effort has tangible operational consequences. Even a single lost station can force months of planning to be abandoned entirely. Modular measuring arrays and floating sensors provide temporary reprieve, yet the ice continually challenges these adaptations, asserting its dominance over human technology. Despite the ingenuity of designs intended to survive collisions or tilts, no deployment remains intact indefinitely. Sensors may drift out of range, topple into leads, or be crushed by sudden ridging, leaving data incomplete. The Arctic's agency is absolute. For every measure of human ingenuity, the ice provides a countermeasure that maintains uncertainty and protects its concealed depths. Researchers accept that loss is built into any field season, an intrinsic property of working on the pack. In contrast to Antarctic ice shelves, the Arctic pack moves unpredictably, crushing and scattering installations in ways that defy long-term planning. While southern stations often occupy relatively stable platforms on massive ice sheets, the central Arctic's sea ice is fragmented, mobile, and continuously reshaped by wind, currents, and temperature. This instability turns routine observation into a race against an environment that cannot be tamed, demonstrating the Arctic's unique ability to erase its record and frustrate human attempts to understand it. Every hour, the ice can create or destroy pathways that were previously mapped, leaving explorers in a constant state of uncertainty. Predictable drift models offer limited guidance, as sudden fractures and storm-driven shifts can render the most careful projections obsolete. Even sophisticated simulations of ice movement cannot anticipate every pressure ridge or flow collision, and unexpected storms can transform calm waters into chaos within hours. Human planning, while informed by decades of observation, is always provisional, a temporary alignment against forces that will inevitably alter or erase the record entirely. Researchers have learned to treat every dataset as provisional, subject to abrupt invalidation by the ice itself. Decades of human effort are scattered, broken, or lost entirely, leaving persistent gaps in knowledge that ensure much of the under-ice world remains inaccessible. The Arctic's shifting ice creates a landscape where the very act of observation is ephemeral. Every field season, every drift station, every measurement array risks disappearance. This continual erasure compounds uncertainty, producing a historical record punctuated by voids and unexplained absences that reinforce the region's mystery and the difficulty of penetrating its frozen veil. The impermanence of human effort, juxtaposed with the ice's patience, amplifies the sense that the Arctic keeps its deepest secrets intentionally, letting only fragments survive. Every broken station, every lost array, is proof that the ice itself decides what will survive and what will be forgotten. The core samples we have yet to take. Drilling crews have long attempted to reach the Arctic's deepest sediment layers, yet most missions end after only a few meters, leaving centuries of environmental history untouched. Each expedition begins with careful planning, yet the harshness of the region imposes immediate limits. Even with specialized rigs and mobile platforms, the combination of thick, shifting ice and extreme cold restricts how much can actually be extracted. For decades, researchers have been tantalized by the promise of these sediments, aware that they could reveal climatic cycles and oceanic patterns going back millennia, but the challenges remain far beyond temporary solutions. Some teams have been forced to abandon promising drill sites after storms or sudden cracks rendered the ice unstable, leaving potentially invaluable cores forever inaccessible. The challenges of stabilizing equipment on drifting ice flows make precise core extraction a rare and technically demanding achievement. Engineers must account for uneven surfaces, cracks that can form without warning, and the constant stress of wind and current. Platforms designed to hold rigs steady often require continuous adjustment, and even slight miscalculations can bend, tilt, or destroy sensitive drilling equipment. The Arctic's movement is slow yet relentless. While it may appear calm, the ice exerts pressures capable of undermining months of preparation. Several attempts at multi-meter cores were cut short because support cables snapped under the combined strain of ice pressure and machinery weight. Past expeditions have returned fragments of ancient sediments, hinting at dramatic climate shifts, but the majority of the central Arctic remains a locked archive. Shallow cores from the edges of the Arctic Ocean have provided glimpses into ice cover fluctuations, ocean circulation changes, and preserved microbial life. These fragments tantalize scientists, offering evidence of patterns unseen elsewhere, yet the data are incomplete, and the story of the pole itself remains largely unread. Even the recovered samples often required complex lab analyses over months to understand what little they revealed, underscoring how inaccessible the remaining deep sediments remain. Specialized rigs require hours of preparation for each attempt, yet even these efforts are at the mercy of sudden fractures and drifting ice. The Arctic's unpredictable nature can turn a carefully staged operation into a scramble for survival. Crews often work in darkness and sub-zero temperatures, adjusting anchors, monitoring flow stability, and checking the integrity of all mechanical components. Even when conditions appear favorable, unforeseen stress on the ice can force teams to halt drilling, retreat, and abandon partially collected cores. Each hour lost in these conditions represents data that may never be captured. Sediment thickness and composition vary unpredictably, with dense layers compacted over millennia, concealing biological and geological clues still hidden from study. Core samples could contain sequences of organic material, trapped gases, or microfossils, each telling a chapter of Earth's environmental history. Yet the depth, density, and unknown variability of these layers make prediction impossible. Drill operators must proceed cautiously, often stopping well short of what could provide the most revealing data. The uncertainty itself contributes to the Arctic's mystique, a reminder that knowledge lies just out of reach. Some estimates suggest the thickest sediment layers in the central Arctic could exceed 100 meters, a daunting target for any expedition. Scientists anticipate that deeper cores could provide direct evidence of ancient ocean currents and ice coverage, yet the extremity of conditions has kept these samples out of reach. Climatic reconstructions rely heavily on indirect evidence, from nearby ice cores to satellite-derived models, but central Arctic sediments remain largely unprobed. Without direct access, questions about the speed of ice retreat, past salinity levels, and the frequency of warm periods linger unanswered. Each unrealized core is a lost opportunity to understand how the Arctic evolved and how it may change in the future. Exploratory data from surrounding seas suggest anomalies, including concentrated organic layers and unusual sediment structures, hinting at mysteries waiting in the central Arctic. Drilling attempts at marginal zones have revealed pockets of dense, finely layered deposits, sometimes rich with fossilized plankton or evidence of sudden environmental shifts. These glimpses suggest that the central basin may contain archives unlike anywhere else on Earth, yet the extreme conditions have prevented full examination. Each discovery from the periphery amplifies the sense of the pole as a vast repository still closed to human inquiry. Transporting equipment, fuel and personnel across the ice introduces logistical limits, preventing long-term operations needed for full-depth sampling. Supply lines are finite, and the remoteness of central Arctic locations magnifies the difficulty of sustaining extended work. Every day of operation must be meticulously planned to account for potential emergencies, weather delays and ice instability. The scale of the challenge limits teams to short windows of activity, and each drill attempt must weigh the risk of equipment loss against the potential scientific gain. Even minor miscalculations in weight distribution can tip a platform into instability, forcing abandonment of a core mid-recovery. Potential hazards, including trapped gases, shifting sediments, and structural instability, make any deep drilling venture perilous. Methane pockets, remnants of ancient organic material decomposed under pressure, could release unexpectedly during drilling. Sediment layers may collapse or compact unevenly, causing mechanical failure. Even the most sophisticated rigs face limits imposed by the environment, with engineers forced to stop operations far short of the deepest and potentially most informative sections. The Arctic's floor remains effectively off-limits, protected by the combination of ice, pressure and uncertainty. Without complete cores, climatologists face gaps in the Arctic record, leaving the chronology of ice formation and retreat uncertain. Models must interpolate between sparse observations, and critical periods may remain undocumented for centuries. This incompleteness affects understanding of global ocean circulation, the timing of past warming events, and the behavior of polar ice under changing climatic conditions. The absence of these data underscores why, despite decades of research, the Arctic still holds so many unanswered questions. The lack of deep cores continues to hinder projections of future environmental change. Indirect methods such as seismic profiling and shallow probes reveal hints of subsurface structures but cannot replace the detail a full core would provide. Sound waves, sonar mapping, and shallow grab samples can indicate layering, density, and composition trends, yet they fail to capture the precise sequence of chemical, biological, and sedimentary records that deep cores provide. These techniques allow informed hypotheses but leave the Central Arctic story largely speculative, as the ice above continues to enforce a natural boundary to exploration. Each untapped layer acts as a frozen archive, preserving millennia of environmental change while concealing its secrets from human investigation. From alternating periods of glacial advance and retreat to the subtle accumulation of organic material, every sedimentary layer is a record waiting to be read. Yet time and again it remains inaccessible, a reminder that the Arctic is both repository and gatekeeper. Even when nearby proxies provide partial insight, the full story of the ice-covered seafloor remains locked in place. Every uncollected meter represents knowledge that will likely remain unknown for decades, if not centuries. Far below the thin veneer of ice that crews can reach, layers of sediment may conceal anomalies that defy current understanding. Ancient currents reversed, sudden collapses recorded, or chemical signatures of climates never predicted by models. Each meter not drilled could contain evidence of events so rare or subtle that they would fundamentally change interpretations of Arctic history. The very uncertainty of what lies beneath adds a spectral quality to the mission. Scientists are acutely aware that the sediments are not merely inert matter, but a silent chronicle of Earth's past, waiting in darkness, indifferent to human curiosity, and perilously preserved only where the ice allows it. Proposed technologies for reaching greater depths exist on paper, yet none have succeeded in the Central Arctic, leaving the region largely unstudied. Ideas ranging from mobile floating rigs to submersible drilling platforms promise potential breakthroughs, but extreme cold drifting ice and logistical constraints have kept these concepts theoretical. Until practical implementation is achieved, the deepest sediments and the history they contain will remain shielded from human eyes and instruments. Time and again, the deepest sediment layers remain uncollected, holding answers to questions scientists cannot yet formulate. Each failed or incomplete attempt emphasizes the formidable combination of ice, pressure, and remoteness that defines the Central Arctic. Even as technology advances, the pole resists, preserving its records in a manner both deliberate and impenetrable. The mystery is not only scientific but existential, reflecting humanity's limited reach in one of the planet's most extreme environments. Every metre of sediment left uncollected is proof that the Arctic's deepest history remains locked beyond our reach. The restricted archive of Arctic data. Vast collections of under-ice surveys exist, yet the majority remain partially inaccessible, leaving large gaps in our understanding of the Arctic's hidden landscapes. The documents, charts and recordings that were once compiled under military and scientific programs sit in archives that are often closed to public researchers, some of them in former Soviet repositories or secure facilities in Western nations. Even when fragments are released, they rarely provide a complete picture, leaving scientists to infer entire geological and hydrological systems from incomplete snapshots. The consequence is a persistent sense that the Arctic holds more than any open dataset can reveal, as though its secrets are deliberately sheltered in paper, tape and magnetic storage, waiting for a moment of disclosure that may never come. Early exploration missions, conducted during the Cold War, produced extensive records that were often classified for decades, shielding significant discoveries from public knowledge. Both Soviet and Western teams charted the under-ice terrain, attempting to map ridges, basins and unknown formations using specialized acoustic devices, gravity measurements and depth-sounding techniques. Many of these operations were designed with national security in mind, meaning that discoveries were recorded but not shared. Only small, sanitized portions of the data have been gradually declassified, offering tantalizing glimpses while the majority remains concealed in government archives. The limited information that trickles out fuels speculation about the features that remain hidden, giving rise to gaps in scientific understanding that grow with every decade. Researchers attempting to reconstruct the region's history must rely on fragmented logs, partial charts, and inconsistent documentation. Efforts to combine declassified files often uncover contradictions. Coordinates that do not align, features described differently in separate surveys, or entire sectors that were omitted entirely. Scientists are forced to work like detectives, cross-referencing scant material with environmental proxies, satellite observations, and shallow surface measurements, all while knowing that much of the truth remains locked behind security protocols. This patchwork approach means that hypotheses about under-ice structures remain provisional, and even widely cited maps are built on incomplete evidence that cannot be fully verified. Mapping efforts revealed ridges, depressions, and irregular formations, but full spatial coverage remains hidden in restricted archives. Published data hint at unusual structures, including elongated valleys and unexpected elevations beneath the ice. Yet the overall layout is impossible to confirm without access to the original files. Some anomalies appear only in the records that remain classified, suggesting the existence of features that could challenge or refine current scientific models of the Arctic seabed. For scientists, the tension between what has been partially revealed and what remains locked away transforms the region into a puzzle that can never be solved completely. National security protocols continue to prevent scientists from accessing complete datasets, forcing reliance on scattered, incomplete sources. Even researchers with official clearance find that files are heavily redacted, sometimes with entire pages, survey notes, or recorded measurements removed. The pattern of omissions implies that sensitive details, whether technological, navigational, or geological, remain off-limits, leaving the under-ice world partially obscured by bureaucracy rather than natural conditions. The secrecy surrounding these archives has persisted long after the missions ended, reinforcing the Arctic's status as a zone of both environmental and institutional inaccessibility. Much of the older material exists in fragile formats, with analog records deteriorating and early digital storage becoming obsolete, further complicating retrieval. Magnetic tapes, paper charts, and early computer files are prone to decay, requiring delicate restoration efforts that few institutions can undertake. In some cases, the original annotations, field notes, or photographic plates have been misplaced or damaged, leaving incomplete stories that can never be fully reconstructed. The physical vulnerability of the archives adds another layer of risk. Even if restrictions were lifted tomorrow, some of the original data might already be lost, irretrievably erasing portions of the Arctic's historical record and deepening the mystery. Without full datasets, researchers turn to indirect observations such as ice thickness measurements, satellite imagery, and environmental proxies to infer subsurface features. These methods provide valuable clues about currents, sediment distribution, and the geometry of under-ice formations, yet they cannot substitute for the granularity of original survey records. Scientists often model hypotheses based on incomplete data, aware that each new discovery could either confirm or overturn assumptions derived from partial information. As a result, every published analysis is provisional, existing within the confines of uncertainty created not by nature alone, but by deliberate restriction. Even released charts display contradictions, missing regions, or inconsistent measurements, creating uncertainty about the Central Arctic's true composition. Features may appear in one dataset but be absent in another, and scales or reference points often differ between missions. These inconsistencies force careful interpretation and highlight the limits of knowledge derived from what is publicly available. Each discrepancy reinforces the impression that the Arctic retains a level of secrecy not dictated by nature alone, while leaving researchers with the constant awareness that the reality beneath the ice may differ dramatically from what the maps suggest. Proprietary surveys and overlapping national claims prevent any single research team from compiling a comprehensive picture of the poles under ice terrain. Different countries have their own maps, records, and digital datasets, each with varying degrees of classification. Collaborative efforts are hampered by both diplomatic considerations and technical incompatibilities, leaving the scientific community dependent on piecemeal insights rather than an integrated understanding. Even international scientific bodies are often constrained to secondary analyses, relying on summaries and aggregated findings rather than primary detailed data. Advances in modern measurement technologies provide higher resolution and extended coverage, yet they cannot replace decades of historical data still withheld. Modern instruments can scan vast areas more efficiently, but the early surveys often recorded phenomena that newer tools have yet to revisit. Missing historical context limits the ability to interpret contemporary observations accurately, and without access to past measurements, scientists are left with partial histories that may misrepresent long-term trends or under-ice structures. The Arctic's topography and subsurface features may therefore remain mischaracterized, with anomalies noted but never fully explained. Partially declassified records occasionally hint at anomalies or unusual structures, offering only tantalizing glimpses of the Arctic's concealed formations. Maps sometimes reveal irregular depressions or subtle linear ridges whose origins are unexplained. Without complete documentation, these features remain enigmatic, their significance speculative. Researchers are left to wonder whether such formations are artifacts of ice dynamics, tectonic activity, or phenomena that have yet to be studied in depth. Each fragmentary glimpse only intensifies the tension between what is known and what remains deliberately obscured. Restricted access has slowed scientific understanding of deep currents, sub-ice topography, and the environmental processes shaping the region. Questions about sediment distribution, water flow beneath thick ice, and the evolution of under-ice features remain largely unanswered. The Arctic, while extensively studied at its margins, continues to withhold a coherent internal narrative, with restricted archives serving as a silent barrier to comprehensive understanding. The interplay between natural challenges and human-imposed secrecy creates a dual layer of inaccessibility that leaves even the most sophisticated models speculative. A fully available archive might reveal previously unknown patterns or features, but for now these insights remain tantalizingly beyond reach. Complete access could allow researchers to validate models, trace historical anomalies, and detect environmental changes with far greater accuracy. Until that happens, the Arctic remains a puzzle composed of fragments, a region whose history and mechanics are partially documented, yet fundamentally incomplete. The withheld records hint at connections, trends, and structures that may forever remain beyond comprehension. Scientific exploration progresses cautiously, constrained by the incompleteness of the historical record and the layers of secrecy surrounding it. Each partial dataset, redacted chart, or inaccessible file reminds researchers that there is a limit to what can be known. The Arctic's under-ice world is not only physically remote, but institutionally shielded, its depths documented more fully in hidden archives than in the field itself. Every analysis and inference is provisional, a step toward understanding a region whose full story has yet to be revealed. Every withheld record and classified map ensures that the Arctic's under-ice world remains a puzzle glimpsed only in fragments.